Welcome, dear listener, to The Sleepy Scientist. This is a place where curiosity drifts gently alongside calm, where science can be both fascinating and soothing, and where the stories of the universe are told slowly enough to help you unwind at the end of the day. Tonight's journey is about water, the element that makes up the oceans, the rain, the clouds, and even a large part of you. Water is older than the Earth itself, a traveller from the stars that has shaped every corner of our planet. Before we begin, I would love to know where you are listening from. Perhaps a quiet bedroom, or maybe with the sound of rain outside the window. Wherever you are, feel free to share it in the comments below. If you enjoy these calm explorations, a like and a subscribe help keep this channel flowing like a steady river, and to those who are already subscribed, thank you sincerely for being part of this journey. Now, I hope this video isn't so interesting that it keeps you wide awake, but if it does, at least the knowledge might ripple through your dreams and leave you with something new by morning. So let us begin. Have you ever wondered how the water in your glass could be billions of years old, older even than the earth beneath your feet? Water has always been more than just a drink or a landscape. It is the quiet architect of our world. In this video, we will follow its story from the birth of the universe to the present day, tracing the hidden connections that make water the most extraordinary substance in existence. Long before oceans sparkled under the sun, water's ingredients were forged in the fiery hearts of stars. Hydrogen, the simplest atom, was born just after the Big Bang, and oxygen emerged much later in stellar furnaces. When these two met in the cold darkness of space, they created molecules that would wander across the cosmos. Some of these droplets of possibility eventually found their way to Earth, settling here to form seas and rivers. But water's story does not end with its arrival. It is a restless traveller, cycling endlessly through forms: vapour, liquid, and ice, sculpting continents, feeding life, and even shaping the air we breathe. Water has been the setting for life's earliest experiments, the stage on which evolution first unfolded, and the force that has carried civilizations through droughts, floods, and discoveries. In the chapters ahead, we will explore how this substance bends the rules of chemistry, why it has been central to every form of life, how it flows through myths and science alike, and what it can teach us about the future. We will drift through deep time, from the icy comets that may have seeded our seas to the rivers that cradled humanity's first cities. As the story unfolds, you may begin to see water not just as something ordinary, but as a timeless companion, one that carries with it the memory of stars, of ancient rains, and of countless lives that have come before. The journey begins far away, long before there was an Earth to call home, in the dark expanses of space where the first drops of water were born. To speak of water is to speak of something ancient, something that has flowed through time longer than the Earth itself. Every drop that rests in a river or a glass has a cosmic biography. Its story begins not in oceans or rain clouds, but in the earliest chapters of the universe, when matter was new and the first stars had yet to shine. The universe began with hydrogen. In those first moments after the Big Bang, nearly all that existed was a vast sea of hydrogen and a touch of helium, along with faint whispers of lithium. There was no oxygen, no carbon, no nitrogen. In other words, none of the elements needed to make water or life. For hundreds of millions of years, the universe remained dark and simple, filled with clouds of gas that drifted through space, waiting for gravity to shape them into something new. The first stars were the alchemists that changed everything. Deep inside their blazing cores, hydrogen atoms fused into helium, releasing energy that made the stars shine. As they aged, heavier elements were forged through nuclear fusion: carbon, oxygen, silicon, iron. Oxygen, one of the two ingredients needed for water, was born in these stellar furnaces. When those stars reached the ends of their lives, many exploded in spectacular supernovae, scattering the elements they had created into the surrounding cosmos. These explosions were both endings and beginnings, seeding the universe with the raw materials for planets, oceans and eventually life. It is in the cooling aftermath of these cosmic fireworks that water molecules could begin to form. When hydrogen atoms met freshly minted oxygen, they bonded into H2O, the same molecule that now flows through your veins. In the cold recesses of interstellar space, tiny dust grains provided surfaces where these atoms could cling together. Ice mantles formed around grains of cosmic dust, and in the darkness between the stars, frozen water became surprisingly common. Modern telescopes, like those that peer in infrared light, have revealed these icy grains scattered throughout molecular clouds, the great nurseries where stars and planets take shape. Imagine drifting inside such a cloud. It is vast and dim, with faint filaments of gas and dust curling like smoke through the void. Within those filaments, simple molecules form: carbon monoxide, ammonia, methane, and most importantly, water. Each molecule may be small, but together they number in unimaginable quantities. In some regions, water makes up as much as half of all the ices present on the grains of dust. Long before Earth existed, the galaxy was already rich in frozen oceans waiting to find a home. Over time, gravity gathered these clouds into denser clumps. New stars ignited, surrounded by swirling disks of gas and dust. Within these disks, planets and comets began to form. Some of the water locked in ice was destroyed by the heat of newborn stars, but much survived in the colder reaches of space. This ancient water became incorporated into icy bodies, comets, and asteroids, the carriers of oceans across the galaxy. When Earth was still young, about 4.5 billion years ago, it was a violent and molten place. Asteroids and comets rained down upon its surface, bringing with them not only rock and metal, but also precious cargo of water ice. Each impact delivered drops of an ocean that would one day cover most of the planet. Some scientists argue that volcanic outgassing, the release of water vapor from deep within Earth, also contributed. But there is strong evidence that at least part of our supply came from these icy messengers of space. Their isotopic signatures, the subtle fingerprints of hydrogen within water molecules, hint that some of the water we drink today was once locked inside a comet orbiting the young sun. To grasp the age of water is to appreciate deep time in a new way. When you sip from a cup, the molecules inside it were assembled in the heart of long-dead stars. They drifted through interstellar clouds, froze onto dust grains, and perhaps spent eons trapped inside a lump of ice hurtling silently through the solar system. That same molecule may have vaporized as a comet approached the sun, condensed again on a cold surface, and finally rained down upon Earth billions of years ago. Every droplet carries this story silently, as if each glass of water is a time capsule from the dawn of creation. What makes water especially remarkable is how widespread it appears to be. Astronomers have detected its spectral signature, the unique pattern of light it absorbs and emits, in distant galaxies, in nebulae, and even in the atmospheres of exoplanets. Water vapor swirls in the disks around young stars, hinting that the formation of oceans may be a common outcome of planetary birth. This suggests that Earth is not unique in receiving such a gift. Worlds across the universe may have their own seas, born of the same cosmic chemistry. The story of water's origin, then, is a story of the universe's creativity. From the simplest atom, hydrogen, and the stellar-born element oxygen, a molecule emerged that would shape entire worlds. It is a small, bent molecule with properties that seem almost whimsical compared to other compounds, but it is also durable. It has persisted across billions of years, never aging, never wearing out, always moving from one state to another. Consider this: the water in your body, in the oceans, in the clouds overhead, is older than the Earth, older than the Sun, older than the solar system itself. It began its journey in stars that lived and died long before our planet formed. In that sense, water is not just ancient, it is immortal. It changes form endlessly, from vapor to liquid to ice, but the molecules themselves endure, carrying with them the memory of their stellar origins. When you pause to think of this, Even the most ordinary glass of water becomes extraordinary. You hold in your hand a fragment of starlight's legacy, the ashes of exploded suns, the frozen whispers of interstellar clouds. Every river, every raindrop, every crashing wave is made of the same cosmic fabric, born of fire carried through darkness and delivered across time to shape a living world. The story of water begins with stars, but it does not end there. Once it arrived on Earth, this cosmic traveller began a new chapter, one that would transform a barren rock into the blue planet we know today. But in every raindrop and every tide, there still lingers the memory of its birth among the stars. 4.5 billion years ago, Earth was far from the calm blue world we see today. Picture instead a restless ball of molten rock, glowing with heat, battered by constant collisions from leftover fragments of the solar system. The young sun was brighter and more temperamental, and the surface of our planet was an unbroken hellscape of fire and stone. Yet hidden in that chaos was the promise of oceans, vast bodies of water that would one day cradle life and paint Earth blue from space. How those oceans arrived, however, is still one of the most fascinating puzzles in planetary science. There are two main contenders for the origin of Earth's water. The first is delivery from above, a steady bombardment of icy comets and asteroids carrying frozen reservoirs from the outer reaches of the solar system. The second is outgassing from below, the release of water vapour trapped deep inside the planet's interior, locked in minerals and carried upward by volcanic activity. Both stories are compelling, and both likely played their part in transforming Earth into a watery world. Comets have long been romanticised as cosmic messengers, icy travellers from the edges of the solar system. Their brilliant tails streak across the night sky, but beneath that beauty lies a practical cargo: frozen water. If enough comets smashed into the early Earth, they could have delivered much of the water that now fills the oceans. The idea seems simple. Icy rocks fall, they melt, and the seas are born. But science is rarely so tidy. When scientists began measuring the isotopic composition of cometary water, specifically the ratio of deuterium to hydrogen, they found something intriguing. Deuterium is a heavier form of hydrogen, and the balance between the two acts like a fingerprint. Many comets have a deuterium to hydrogen ratio that does not quite match Earth's oceans. Some are too heavy, suggesting their contribution was smaller than once imagined. Still, not all comets are the same. A few, such as Comet 103P/Hartley 2, have water that closely matches Earth's signature, hinting that at least some of our oceans may indeed have been delivered from the icy outskirts of the solar system. Asteroids, often overshadowed by their more dramatic comet cousins, may actually have been even more important. These rocky bodies, particularly carbonaceous chondrites, contain significant amounts of water locked in their minerals. Unlike comets, they originated closer to the Sun, making their delivery more plausible in terms of orbital dynamics. Their isotopic signatures line up neatly with Earth's oceans, suggesting that asteroids could have been the true champions in seeding our planet with water. Meanwhile, deep within Earth itself, another process was unfolding. When the planet first formed, it accreted not just rock and metal, but also materials that contained water bound within their crystal structures. As Earth's interior heated and churned, much of that water was released in the form of steam through volcanic eruptions. Imagine countless volcanoes across a molten landscape, spewing gases into a toxic sky. Carbon dioxide, nitrogen, sulfur compounds, and crucially, water vapour filled the air. Over millions of years, this outgassing could have built a thick, steam-laden atmosphere. Eventually, as Earth's surface cooled, that vapour condensed into liquid, falling as relentless rain. For thousands, perhaps millions of years, it poured without end. Drop after drop, storm after storm, the water collected in the lowest basins, forming the first oceans. It must have been an astonishing transformation. A planet once red hot and glowing, scorched and cracked, slowly cloaked in shimmering blue. This rain was no gentle drizzle. The young Earth still endured impacts from space, each one sending shock waves across the surface, boiling away seas and vaporizing water into the sky, only for the cycle to begin again. Oceans may have filled and evaporated many times before finally stabilizing, yet by around 4 billion years ago, evidence suggests large, persistent bodies of water covered much of Earth's surface. The violent world had given way to one that could reflect the light of the sun in shades of blue. To walk along the shore of that first ocean, if one could time travel, would have been a surreal experience. The air was thick with carbon dioxide, unbreathable by modern lungs. The seas were likely acidic, churning with dissolved minerals. The land was barren, without a blade of grass or a single tree. Yet despite this alien quality, the oceans glittered under the sun, a familiar sight in an otherwise unfamiliar world. They were the stage on which life's first experiments would soon unfold. The debate between cometary delivery and volcanic outgassing is not fully resolved, and it may never lean entirely to one side. The truth is probably a mixture of both. Some water rained down from space carried by asteroids and perhaps the occasional comet. Some emerged from deep inside the planet, liberated by volcanic breath. Together, these sources filled the basins and transformed Earth from a fiery orb into the ocean world we recognize today. One of the remarkable things about this transformation is how quickly it happened in geological terms. From fiery birth to watery stability, only a few 100 million years passed. That is less than 10% of Earth's age, a blink in cosmic time. Once oceans formed, they became persistent, surviving asteroid impacts, supervolcanoes and ice ages. They cycled endlessly but remained, anchoring the climate and shaping the surface. If you could stand in space and watch the change unfold, it would be breathtaking. First, a glowing rock spinning under the sun, its surface alive with magma oceans and erupting mountains. Then, clouds forming, thick and heavy with steam. Rain falling, steaming on contact with hot stone but falling still over and over. Eventually water gathering, spreading, reflecting sunlight until the planet itself glowed blue. That blue has endured ever since, a signature visible across the galaxy. Earth's oceans are, in a sense, the planet's autobiography written in liquid. They carry the memory of comets and asteroids, of volcanoes and rainstorms that lasted longer than human imagination can easily grasp. They are reminders that creation is rarely a single act, but rather a weaving together of many sources and forces. When you gaze at the ocean today, stretching endlessly toward the horizon, you are looking at a blend of two origins: water, born in the cold of space, and water exhaled from the fiery lungs of Earth itself. Both journeys converge to fill the seas, setting the stage for every wave, every storm, and every living thing that followed. What began as fire and stone became a world of water, and in that shift lay the foundation for life itself, a transformation so complete that Earth would forever after be known as the Blue Planet. The oceans of early Earth were not just vast stretches of water, they were enormous laboratories, restless places where chemistry experimented endlessly. In their waves and depths, the simple elements forged in stars and delivered by comets mingled in countless combinations. Out of this watery chemistry, life began its improbable story. To understand why, it helps to look at water not simply as a liquid, but as the stage, the solvent, and even the silent participant in the earliest reactions that made life possible. Chemistry thrives on contact. For atoms and molecules to link, they must collide, trade electrons, and settle into new arrangements. Water, with its unusual properties, provided the perfect medium for such encounters. It dissolves salts and minerals, it suspends organic molecules, and it allows them to move freely enough to meet, but not so chaotically, that everything dissolves into chaos. In other words, water creates just the right balance between stability and mobility. Without it, the dance of molecules would have been far too sluggish or far too violent to sustain the delicate steps needed to build life. The oceans of early Earth contained a cocktail of ingredients. From volcanic gases bubbled carbon dioxide, nitrogen and hydrogen sulfide. Lightning in stormy skies may have sparked new organic molecules from methane and ammonia. Hydrothermal vents at the bottom of the sea spewed minerals and heat, enriching the chemistry further. These vents in particular are thought to have been crucial. They create gradients, differences in temperature, pressure and chemical concentration, that drive reactions forward. Where hot mineral-rich water meets cold seawater, energy is released, and with it, the possibility of building complexity from simplicity. Imagine towering chimneys of black smoke rising from the seafloor, surrounded by shimmering plumes of heat. These hydrothermal vents are alive with mineral deposits that act almost like natural catalysts. Iron, nickel, and other metals create surfaces where carbon compounds can assemble into more elaborate molecules. It is as if nature had built millions of tiny laboratories across the ocean floor, each running experiments for millions of years. One of the great questions of science is whether life began in such vent environments or in the so-called primordial soup, a rich broth of organic molecules spread across shallow seas or tidal pools. The soup theory suggests that sunlight, lightning and volcanic gases could have combined to cook up amino acids and other essential building blocks. Laboratory experiments, most famously the Miller-Urey experiment of the 1950s, showed that under the right conditions, simple mixtures of gases can indeed produce amino acids, the components of proteins. Whether this soup alone could have organized into something as complex as life is debated, but it shows how naturally such chemistry can arise in water-rich environments. What makes water indispensable in all of this is its peculiar chemistry. A water molecule is small and deceptively simple, but its bent shape and polar nature allow it to form hydrogen bonds. These weak attractions between molecules create an environment where larger molecules can fold, twist, and stabilize into functional shapes. Proteins, for instance, owe their complex structures to the influence of surrounding water. Without water, the delicate architecture of life's molecules would collapse. Water also plays a vital role in energy transfer. In cells today, reactions often involve breaking or forming bonds with water, processes known as hydrolysis and condensation. It is not just a passive stage. Water actively participates, shuttling pieces of molecules and enabling reactions that would otherwise stall. On the prebiotic Earth, this chemistry may have been the key to stringing together nucleotides into RNA, or amino acids into proteins, steps essential to bridging the gap between mere chemistry and biology. Consider the possibility of RNA molecules emerging in these watery settings. RNA is remarkable because it can both store information and catalyze reactions. It may have been one of the earliest self-sustaining molecules capable of copying itself and evolving. But RNA is fragile. Without a solvent like water to cushion its formation and maintain its bonds, it would not have lasted. The oceans offered the ideal environment, protecting these delicate chains and allowing them to accumulate. There is also the matter of cycles. Life is not built from one-off reactions, but from processes that repeat and sustain themselves. Water's ability to cycle endlessly, evaporating, condensing, and raining again, may have concentrated key molecules in shallow pools or along coastlines. Repeated wetting and drying could have encouraged simple molecules to link into longer chains. Each cycle was another chance for chemistry to take a step toward biology. In reflecting on why water is so perfectly suited for life, some scientists have called it the universal solvent. It dissolves more substances than any other liquid, creating a playground where atoms and molecules are constantly encountering each other. That versatility gave the early Earth's oceans their power. No matter what building blocks arrived, whether from volcanic gases, lightning strikes, or asteroid impacts, water provided the medium where they could meet, mingle, and evolve into something new. It is humbling to imagine that the first flicker of life might have begun as a cluster of molecules floating in a droplet, perhaps near a vent or within a shallow tide pool warmed by the sun. From the perspective of chemistry, there is no magic in this, only the natural outcome of time, energy, and water's patient work. Yet from the perspective of life itself, it is miraculous. Out of countless reactions, some arrangement of molecules stumbled upon self-replication, and the rest is history. The debate between hydrothermal vents and primordial soup is ongoing, but they may not be mutually exclusive. Life may have had multiple possible starting points, with different environments testing different recipes until one succeeded. What unites all these scenarios is water. It was present in every theory, every experiment, every imagined setting where the spark of life could catch. Every living thing today carries a reminder of those beginnings. Our cells are tiny oceans, each filled with water where chemistry continues to hum along. The salts in our blood echo the composition of ancient seas. The dependence of every organism on water is not just a coincidence but a memory, carried forward from the moment when chemistry first became life. When you look at a glass of water, you're not just seeing a drink. You're looking at the medium that transformed a barren world into a living one. It is the same liquid that cradled fragile strands of RNA, that cushioned the first proteins, that held together the earliest membranes. Every living creature is, in a way, a monument to water's extraordinary chemistry. In the beginning there was fire and stone, but it was water that took those raw ingredients and began to stir them, slowly, patiently, until something new emerged. From the depths of the ocean floor to the shimmer of tidal pools, water was the quiet chemist, working without hurry, shaping the first sparks of life. Water is often imagined as a surface phenomenon, something that fills oceans, rivers and clouds drifting across the sky. Yet Earth's story of water runs far deeper than what is visible. Beneath our feet lies an unseen cycle, one that moves slowly but persistently, circulating water not just across the seas and skies, but through the very rocks of the planet. This hidden cycle links surface life to the deep interior, acting like a planetary heartbeat that has pulsed for billions of years. The familiar water cycle is easy to picture. Sunlight warms the oceans, water evaporates, rises into the atmosphere, condenses into clouds, and returns as rain or snow. Rivers carry it back to the sea, and the process repeats endlessly. This cycle is swift, often measured in days, weeks, or seasons. But beyond this surface rhythm is another slower cycle, the geologic water cycle, which carries water between the oceans and the mantle over millions of years. The mantle may seem like the last place to look for water. It is hot, dense rock lying hundreds of kilometers beneath the surface. But minerals in the mantle can trap water in surprising quantities, not as liquid pools or underground lakes, but as molecules locked into crystal structures. Minerals like ringwoodite and wadsleyite are capable of holding significant amounts of hydroxyl, a form of water bound within their lattices. Though invisible, this stored water is vast. Some estimates suggest that the mantle may contain as much water as all the oceans combined, hidden away in solid rock. The way water moves into the mantle begins at the ocean floor. Where tectonic plates spread apart, volcanic activity creates new crust, rich with basalt that soaks up seawater. This water penetrates through cracks, reacting with minerals to form hydrated rocks. Over time, as tectonic plates drift, these water-laden slabs are pushed back into Earth's interior at subduction zones. As they sink, the pressure and heat grow intense, and the water bound within the rocks is eventually released. This release is not gentle. It fuels volcanic activity, melts rocks, and helps drive the formation of magma. In this way, water acts as both passenger and driver in the deep earth. It is carried into the mantle by sinking slabs of crust, then returned to the surface through volcanic eruptions and the slow outgassing of magma. Each volcanic plume is more than fire and ash. It is also the exhalation of water that has travelled a cycle spanning millions of years. The clouds above a volcano are not only weather, but whispers of the deep earth returning its stored cargo to the skies. This deep circulation matters for more than geology. It regulates the composition of the atmosphere, balancing the gases over geological timescales. It influences the stability of the oceans, preventing them from slowly draining into the mantle or evaporating entirely into space. It even shapes the planet's long-term climate. Without this slow, steady cycle, Earth might not have maintained its stable oceans for billions of years, and life may never have had the chance to flourish. Consider how astonishing it is that water can exist in so many forms and places, as vapour above mountains, as liquid in rivers, as ice in polar caps, and as locked molecules deep within mantle rock. It is as though Earth has found every possible way to store and circulate its water, ensuring that no single catastrophe can strip it away entirely. Even when surface oceans boil off during massive impacts or global freezes lock them in ice, the mantle still holds reserves, ready to breathe them back over time. The evidence for this deep reservoir is not just theoretical. In 2014, scientists analysed a diamond from deep within the Earth that contained ringwoodite with water trapped inside. This tiny inclusion, less than a millimetre wide, revealed that the mantle transition zone, lying between 400 and 600 kilometres deep, may be saturated with water-bearing minerals. It was a small stone with a big story, confirming that Earth's hidden oceans are not just speculation but reality. The timescales of the deep water cycle are staggering. While a raindrop may complete its journey from cloud to sea in a matter of weeks, a molecule of water pulled into a subducting slab might not resurface for tens of millions of years. This cycle is slow, but its influence is profound. It maintains the balance of surface water, prevents runaway changes, and provides a long-term stability that life depends on. It is in many ways Earth's silent insurance policy. The deep water cycle also reminds us that Earth is not static. Beneath our quiet landscapes, entire oceans worth of water are being shuttled downward and upward, woven into the ceaseless motion of tectonic plates. Every earthquake and every volcanic eruption is a reminder that this cycle is still very much alive, a dynamic system that has persisted since the earliest days of the planet. It is tempting to think of oceans as eternal, as though they have always been here in their present form. But the truth is more dynamic. Oceans shrink and grow, influenced not just by surface climate but by these deep exchanges. When more water is locked in mantle minerals, sea levels fall. When more is released through volcanism, oceans rise. Over eons, this hidden rhythm has quietly sculpted the conditions on Earth's surface. There is also a poetic symmetry to this cycle. Water, the agent that carved valleys and nurtured life, also seeps into the planet's interior, altering the rocks themselves. It lubricates faults, softens minerals, and reduces the melting point of rocks, making it a key player in plate tectonics. Without water, the continents might never have drifted as they do, and Earth's surface would be unrecognisable. The slow pulse of the deep water cycle is entwined with the restless movements of continents and the changing face of the world. When viewed this way, Earth itself seems alive, with water as its bloodstream. The shallow cycle of rain and rivers is like quick breathing, while the deep geologic cycle is the steady heartbeat, slower but just as vital. Both rhythms work together to sustain the balance that has kept Earth habitable across deep time. The next time you stand by the ocean, it is easy to think of all that water as simply surface. But beneath the waves lies a second ocean, hidden in stone, silently circulating through the planet's mantle. Together, the visible and the hidden cycles weave a story of endurance. Earth has not only kept its water, it has recycled it, protected it, and folded it into every layer of its being. To drink a glass of water is to take part in this planetary rhythm. Some of those molecules may have fallen as rain last week. Others may have been released from a volcanic vent millions of years ago, Still others might have been trapped deep within minerals since before the first life stirred in the seas. Each sip carries with it the heartbeat of a planet that has never stopped cycling its most precious element. Water is not only a constant companion in Earth's history, but also the great regulator, the force that has driven the planet through dramatic swings of climate. Across billions of years, Earth has seen extremes that stretch the imagination, times when the planet was almost entirely frozen over from pole to pole, and others when tropical seas washed over continents and there was barely an ice crystal to be found. These cycles of ice ages and hothouse climates are reminders of how profoundly water shapes the destiny of a world. Let's begin with a scenario so dramatic it sounds like science fiction: Snowball Earth. Around 700 million years ago, evidence suggests that glaciers extended all the way to the equator. The oceans froze nearly solid, locked under thick sheets of ice. If you had been alive then, you might have looked out at Earth from space and seen a gleaming white sphere, a planet almost indistinguishable from an enormous frozen moon. Yet this was not fiction. Geological records such as glacial deposits found in tropical latitudes show that Earth endured multiple global-scale ice ages. How could this happen on a planet warmed by the sun? The answer lies in the delicate balance between sunlight, atmosphere, and water. Ice is reflective, bouncing much of the sun's energy back into space. As glaciers spread, more light was reflected, causing further cooling in a runaway feedback loop. Before long, Earth tipped into a deep freeze, its oceans covered in ice possibly hundreds of meters thick. Life clung on in refuges, perhaps beneath the ice in pockets of liquid water warmed by geothermal heat or around hydrothermal vents. Snowball Earth was not permanent. Volcanic activity continued beneath the icy surface, belching carbon dioxide into the atmosphere. With oceans sealed under ice, that carbon dioxide could not be reabsorbed by weathering or dissolved in seawater, so it accumulated. Over millions of years, greenhouse gases built up to such high levels that they eventually broke the cycle, trapping enough heat to melt the ice. When the thaw came, it must have been cataclysmic. Gigantic floods roared across the continents, and the oceans opened once again. This swing from frozen to thawed illustrates the immense power of water, both as ice reflecting sunlight and as vapour amplifying greenhouse warming. If Snowball Earth represents one extreme, then hothouse climates stand at the other. Throughout Earth's past, there were times when global temperatures soared and the poles were free of ice. One such period was the Cretaceous, roughly 100 million years ago, when dinosaurs roamed a world far warmer than today. Sea levels were higher, tropical forests reached into polar regions, and warm, shallow seas covered much of the continents. Fossilized palm trees found in what is now Alaska speak to this remarkable warmth. What drove such hothouse conditions? Again, water played a starring role. High levels of carbon dioxide from volcanic activity trapped heat, while the absence of reflective ice allowed more sunlight to be absorbed. Warmer oceans evaporated more water, and since water vapour itself is a greenhouse gas, this created another powerful feedback loop. Clouds formed, storms raged, and Earth became a steamy, humid world. Far from being just a passive backdrop, water was both amplifier and stabilizer, carrying heat across the globe through currents and storms. Between these extremes, Earth has seen repeated glacial cycles over the past 2.5 million years, the ice ages most familiar to us. These are shorter and less extreme than Snowball Earth, but still dramatic. Sheets of ice advanced and retreated across North America, Europe, and Asia, carving valleys, shaping mountains, and creating the landscapes we recognize today. At the height of the last glacial maximum, around 20,000 years ago, ice sheets more than 3 kilometers thick buried much of the northern hemisphere. Sea levels dropped by more than 100 meters, exposing vast tracts of land that humans and animals used as migration routes. The rhythm of these ice ages is guided by subtle changes in Earth's orbit and tilt, known as Milankovitch cycles. These small variations alter how sunlight is distributed across the planet. Water responds to these changes with great sensitivity. More snow and ice increase reflectivity, encouraging further cooling. Melting reverses the effect, allowing the planet to warm again. The cycle is a slow pendulum, swinging back and forth over tens of thousands of years, with water as both passenger and engine. These glacial eras remind us that water is an architect of landscapes. When glaciers grind across rock, they leave behind valleys, fjords, and polished stones. When they retreat, they release torrents of meltwater, feeding rivers and lakes. Entire ecosystems and human societies have been shaped by these advances and retreats. Even today, the Great Lakes of North America are legacies of glacial carving and melting. The contrast between frozen Earth and Hothouse Earth might seem extreme, but both share a common truth. Water is the planet's thermostat. In one form, as ice, it cools the planet by reflecting light. In another, as vapor, it warms the planet by trapping heat. As liquid, it carries warmth through currents, distributing energy from the equator to the poles. Earth's climate is, in essence, water in motion. It is worth reflecting on how resilient life has been through these swings. During Snowball Earth, life may have been reduced to small microbial pockets, yet it endured. During Hothouse periods, tropical conditions flourished even in polar regions. Life adapted, survived, and even thrived, evolving in step with the shifting climate. The extremes of water's influence may have been harsh, but they were also creative forces, nudging evolution forward in new directions. One striking example is the Cambrian explosion, which followed soon after the last great Snowball Earth events. The thaw released floods of nutrients into the oceans, fueling an evolutionary burst that gave rise to the ancestors of nearly all modern animals. It is tempting to imagine that without such extreme ice ages, life may not have diversified in the same way. Water, in freezing and thawing, may have acted as the Great Reset button, clearing the stage and allowing new forms to emerge. Hothouse conditions, too, had profound impacts. The warm, shallow seas of the Cretaceous nurtured coral reefs and diverse marine life. The lush forests of the time stored enormous amounts of carbon, influencing the balance of gases in the atmosphere. When conditions shifted again, many species disappeared, but others rose to take their place. Each climate swing left fingerprints not just in rocks and ice cores, but in the very fabric of biology. Today, scientists study these past extremes to better understand our present. Ice cores drilled from Antarctica contain tiny bubbles of ancient air, revealing atmospheric compositions and temperatures stretching back hundreds of thousands of years. Rocks from ancient glaciations tell us where ice once reached, even near the equator. Together, they show that water has always been the main actor in Earth's climate theatre. The story of water across geological time is dramatic, almost theatrical. It has frozen the planet solid, drowned continents beneath tropical seas, and marched glaciers across the land like slow armies of ice. Yet through all these transformations, water has also been steady, never leaving but simply shifting form. It is the element of change and the element of continuity, reminding us that stability is not stillness, but balance in motion. When you look out at the world today, with its glaciers melting and seas rising, it is natural to feel that the climate is fragile. But in truth, Earth has always been dynamic, always shifting between extremes. What matters is how quickly those shifts happen, and how life adapts in response. The lesson of geological time is that water will continue to regulate, to reshape, to push and pull the planet's climate. The only question is how humanity will live within that rhythm. Across billions of years, water has proven itself the ultimate sculptor, capable of turning a fiery young world into a frozen orb or a steaming greenhouse. It reflects sunlight, traps heat, carves stone, and feeds rivers. It is the pulse of climate, the architect of landscapes, and the silent force behind evolution's greatest leaps. Earth's history of ice ages and fire worlds is not just a record of extremes, it is a testament to water's endless power to transform the face of a planet. If mountains are the bones of the Earth, then rivers are its sculptors, patiently carving, smoothing, and carrying away the excess. A single river may look delicate compared to the immensity of a continent, but given time, water has the persistence to cut valleys, dig canyons, and rearrange landscapes on a grand scale. What we see today in winding channels and wide deltas is the work of liquid patience, a process measured not in years but in millions of years. Erosion is at the heart of this transformation. When rain falls on mountains, droplets gather into rivulets and streams, which merge into rivers. As they move downhill, they pick up sediment, grains of sand, pebbles, sometimes boulders, and carry them along. This cargo acts like nature's sandpaper, grinding down the rock beneath, slowly reshaping the land. The water itself dissolves minerals, pulling ions into solution and transporting them to distant seas. Bit by bit, the mountains are worn away, their height traded for the sediment that will one day form new landscapes elsewhere. The power of rivers to shape terrain can be seen most dramatically in canyons. The Grand Canyon is the most famous, a colossal scar stretching over 400 kilometers, cut by the Colorado River over millions of years. Standing on its edge, one can see nearly 2 billion years of geological history exposed in layer upon layer of rock. Each stratum tells a story. Ancient seas, deserts, and swamps, all carved open by the patient persistence of flowing water. It is humbling to realize that what looks like a static monument is actually the result of endless motion. But rivers do not only cut downward, they also build outward. As rivers reach flatter ground, their currents slow, and they begin to deposit the sediment they once carried. This creates floodplains, rich with fertile soil, where civilizations have thrived for thousands of years. Further downstream, where rivers meet the sea, deltas form. These are landscapes of branching channels and marshes, constantly shifting as the river delivers fresh loads of sediment. The Nile Delta, the Mississippi Delta, the Ganges-Brahmaputra Delta, all are products of water's restless creativity. They are nurseries for life and hubs for human culture, formed entirely by the accumulation of countless grains carried from faraway mountains. The shaping power of rivers can also be subtle. A meandering stream on a flat plain seems lazy, but even its curves are instruments of change. As water bends, it erodes the outer bank and deposits sediment on the inner bank, causing the river to shift and snake across the land. Over centuries, these meanders can become oxbow lakes, crescent-shaped remnants of old channels. The landscape becomes a record of the river's wandering, like the doodles of water left behind as it experiments with new paths. Water does not hurry, yet it achieves more than the strongest forces. A glacier can bulldoze valleys, and an earthquake can shatter mountains, but rivers refine the results, sculpting the raw forms into smooth valleys and broad basins. Their patience is their power. Give a river a mountain, and it will eventually carry it to the sea. One of the marvels of this process is its recycling. The sediment rivers carry is not lost but reused. Grains of sand carried from granite peaks may settle in a delta, compact into sandstone, and later be uplifted as new mountains. The journey of a single mineral grain can span billions of years, carried back and forth by rivers that never cease their work. This constant movement ties together distant parts of the world. The soil beneath your feet may once have been part of a mountain range half a continent away. The Amazon River offers a striking example of scale. It drains an area larger than the entire United States, carrying more fresh water than any other river on Earth. Each day it delivers vast quantities of sediment to the Atlantic Ocean, forming a plume visible from space. The very shape of South America has been influenced by this river system, as the Andes shed their mass grain by grain into the Amazon basin. Without rivers like this, continents would remain sharp and rugged, but with them the land is reshaped into plains, wetlands and coasts. Rivers also create opportunities for life. Freshwater habitats teem with fish, amphibians and insects. Floodplains enrich soils with nutrients, supporting forests and agriculture. Deltas provide shelter for countless species of birds and marine life. Life has always followed rivers, not only because they provide water, but because they continually renew the land. Even human history is inseparable from rivers. The Nile, the Indus, the Yangtze, the Tigris and Euphrates. Each of these rivers was both a geographic feature and a lifeline, shaping where cities rose and how cultures spread. From a scientific perspective, rivers are also storytellers. By studying the sediments they carry, geologists can reconstruct climates and environments of the past. Grains of sand reveal the type of rock they came from. Isotopes of oxygen in shells deposited by rivers reveal patterns of rainfall and temperature. A river is not only a sculptor but an archivist, preserving within its deposits the memory of the landscapes it has passed through. It is worth noting that rivers are not eternal in form. They shift courses, abandon old channels and carve new ones. Over geological time, entire drainage systems reorganize themselves, sometimes dramatically. The Mississippi River, for instance, has changed course multiple times, leaving behind abandoned valleys across the plains. Each change is a reminder that even the most dependable-seeming river is an agent of change, not permanence. The beauty of rivers is that they work at all scales. A small creek trickling through a forest carves its banks just as surely as the Amazon sculpts continents. The principle is the same: water flowing downhill, carrying away the high places and filling the low. Over time, those tiny drops add up to monumental results. There is something comforting in that persistence, a reminder that transformation does not always require speed or violence, only time and patience. Even deserts, seemingly devoid of rivers, carry their imprint. Dry canyons and wadis are remnants of ancient streams that once flowed when climates were wetter. Flash floods may occasionally remind the land of water's power, carving channels in mere hours that will stand dry for centuries. The absence of water in these places only highlights how transformative it has been in the past. When standing at the edge of a canyon, or gazing at the fan-shaped spread of a delta, it is easy to forget that all of this was created by something as simple and ordinary as water following gravity's pull. Yet therein lies the magic. The greatest landscapes of Earth are not always the result of sudden catastrophes, but of ordinary processes repeated endlessly. Rivers are proof that patience multiplied by time can move mountains. In the end, rivers are not just features of geography. They are living systems connecting sky, mountain, and sea in one continuous flow. They shape continents, nurture life, and tell stories written in stone and sand. To follow a river's course is to watch Earth sculpt itself, grain by grain, until what was once rugged and raw becomes graceful and enduring. Each river is a reminder that water never rests, and through its endless journey, the face of the planet is forever being reshaped. The oceans are often thought of as vast blue spaces, places where waves roll and creatures swim, but they are also the great regulators of Earth's climate. Without them, the planet would swing wildly between extremes of heat and cold. With them, the climate is tempered, buffered by an immense system that moves energy, moisture, and even gases around the globe. To call the oceans Earth's thermostat is not poetic exaggeration but scientific truth. Water has a remarkable capacity to store heat. Compared to air or rock, it takes much more energy to change its temperature. This means that the oceans act as giant heat reservoirs, soaking up warmth in summer and releasing it in winter, smoothing out the annual swings that would otherwise make climates far harsher. Coastal regions feel this moderation most keenly. A city by the sea enjoys milder winters and cooler summers than one far inland at the same latitude, all thanks to the ocean's steadying hand. But the oceans do more than store heat. They transport it. Warm water from the tropics is constantly on the move toward the poles, while cold water sinks and flows back toward the equator. This global conveyor belt of currents, known as thermohaline circulation, redistributes energy across the planet. It is powered by differences in temperature and salinity, hence the name thermo for heat and haline for salt. As water cools near the poles, it becomes denser and sinks, pulling surface water behind it. In this way, the oceans act as giant arteries, carrying warmth across thousands of kilometers. The Gulf Stream is the most famous of these currents. Originating in the Gulf of Mexico, it sweeps up the eastern coast of North America before heading across the Atlantic toward Europe. It carries so much heat that it effectively warms entire continents. London, for instance, sits farther north than Calgary, Canada, yet has milder winters because the Gulf Stream delivers warmth to the coasts of Europe. Without this current, much of northern Europe might endure winters as severe as Siberia. Currents do not just shape regional climates, they also influence weather patterns across the globe. Consider El Niño, the periodic warming of surface waters in the central and eastern Pacific Ocean. When it occurs, trade winds weaken, warm water spreads eastward, and the ripple effects are felt worldwide. South America often experiences heavy rains and floods, while parts of Australia and Southeast Asia face drought. North America can see altered storm tracks and unusual temperature swings. La Niña, the counterpart characterized by cooler Pacific waters, brings the opposite effects. Together, these cycles are reminders of how the ocean's moods reverberate across the planet. Beyond these well-known phenomena, the oceans participate in countless other climate processes. They generate monsoons, power hurricanes, and store vast amounts of carbon dioxide. In fact, the oceans absorb roughly a quarter of the carbon dioxide released by human activity each year. Phytoplankton, the microscopic plants drifting in the sunlit surface, use sunlight and carbon dioxide to grow, quietly regulating the atmosphere while forming the base of the marine food chain. Without the oceans acting as this sink, the build-up of greenhouse gases would be even more dramatic. Yet this role as a buffer comes with limits. The more heat the oceans absorb, the more they expand, contributing to rising sea levels. As they take in more carbon dioxide, they become more acidic, threatening corals, shellfish, and countless other organisms. The thermostat works, but it is not indestructible. Like any finely tuned system, it can be thrown off balance. Still, the ingenuity of the oceans in maintaining stability is breathtaking. Picture the entire planet as a heat engine, with the equator receiving more solar energy than the poles. Left unchecked, this imbalance would lead to unbearable temperatures in the tropics and permanent deep freezes in the polar regions. The oceans redistribute this heat, flattening the extremes, carrying energy across hemispheres and seasons alike. Winds play their part too, but water, with its immense capacity and circulation, is the heavy lifter. The scale of this system is staggering. A single major current can move more water than all the world's rivers combined. The thermohaline circulation operates like a global conveyor belt, taking centuries to complete a full loop. Warm water that drifts northward today may not return to the surface until the distant future, somewhere near Antarctica. The oceans think in timescales far longer than human lives, patiently adjusting the climate one slow circulation at a time. Even the smallest details of climate are touched by this watery engine. The fog that clings to coastlines, the seasonal rains that feed crops, the steady breezes that make some harbours favourable for sailing, all are influenced by the interplay of sea and sky. Without this regulation, Earth would not be the same gentle cradle it has been for life. The ocean's role in climate can also be seen in moments of disruption. When the Gulf Stream weakens, as some evidence suggests it has in recent decades, weather patterns shift. Storms intensify in some regions, while droughts deepen in others. Ice melt from Greenland adds fresh water to the North Atlantic, changing the salinity that drives circulation. This shows how delicate the balance can be, and how easily human activity can tilt the system. From another perspective, the oceans are the memory of Earth's climate. Layers of sediment on the seafloor preserve records of past temperatures and currents. Tiny shells of plankton buried over millennia carry chemical signatures that reveal how warm or cold the waters were when they lived. By reading these records, scientists have pieced together stories of past ice ages, warm periods, and sudden shifts. The oceans not only regulate the present, but also hold the history of climates long gone. To stand on a beach and watch the waves is to see only the surface of an immense and intricate machine. Beneath those waves, water is moving across entire oceans, carrying heat and energy in silent loops that shape the air we breathe and the weather we experience. It is both gentle and immense, a force that cools, warms, and stabilizes the earth. Perhaps the most poetic way to think of it is this: the oceans breathe for the planet. They inhale heat, gases, and energy, and they exhale them back in cycles that span years to centuries. Their breath keeps Earth's climate alive, balanced, and dynamic. And as long as they continue to flow and circulate, the planet will never be still but always in motion, always finding equilibrium through the endless rhythm of water. Water may look ordinary, but in the realm of chemistry it is a delightful troublemaker, a molecule that routinely breaks the rules and somehow gets away with it. If other compounds behaved as water does, the world would be unrecognizable. We often think of H2O as simple, just two hydrogens and one oxygen. Yet its structure gives it quirks that shape everything from the weather above our heads to the cells inside our bodies. Without those quirks, life as we know it would simply not exist. At the heart of water's odd behavior lies its shape. The oxygen atom sits in the center, with two hydrogen atoms attached at an angle of about 104 degrees. This bent structure creates polarity, meaning one side of the molecule is slightly negative while the other side is slightly positive. It is as if the molecule has a tiny magnetic personality, eager to link arms with its neighbours. The result is hydrogen bonding, a weak but pervasive attraction between water molecules that gives rise to many of water's strange properties. Take surface tension, for example. Thanks to hydrogen bonds, water molecules at the surface cling together tightly, creating an invisible skin. This is why small insects like water striders can walk on ponds without sinking. It's also why drops of water form beads on a leaf, or why raindrops appear as spheres clinging to a window pane. The cohesion is so strong that you can slightly overfill a glass and the water will mound above the rim, refusing to spill until gravity finally wins. Another rule that water gleefully ignores is density. For most substances, the solid form is denser than the liquid, which is why solids sink in their melted versions. But water turns this rule on its head. Ice floats. The reason again lies in hydrogen bonding. As water freezes, the molecules arrange themselves into a crystalline lattice, held apart by bonds that leave empty space. This structure makes ice less dense than liquid water. The consequence is profound. Lakes and oceans freeze from the top down rather than from the bottom up. Ice forms a protective lid that insulates the water beneath, allowing fish and other life to survive through winter. Without this anomaly, cold seasons could wipe out aquatic ecosystems entirely. Water also defies expectations when it comes to its boiling and melting points. Molecules of similar size, such as hydrogen sulfide or hydrogen selenide, are gases at room temperature. By the logic of periodic trends, water should be a gas too. Instead, it remains liquid over a wide range of temperatures. The reason, yet again, is hydrogen bonding, which holds the molecules together more strongly than in most other small compounds. These bonds demand extra energy to break, raising the boiling point and keeping water liquid under conditions where it should, by all rights, have evaporated. If water followed the rules, rivers and oceans would vanish in a puff of steam. Then there is its extraordinary heat capacity. Water can absorb large amounts of energy before warming significantly. This property stabilizes climates, moderates weather, and makes life comfortable. A desert without water heats and cools rapidly, but a coastal region experiences mild swings because the ocean acts as a buffer. Inside our bodies, Water's high heat capacity helps regulate temperature, allowing us to survive in changing environments without overheating or freezing with every fluctuation. The list of oddities continues. Water is an excellent solvent, dissolving more substances than any other liquid. Its polarity allows it to surround ions and molecules, prying them apart and carrying them into solution. Salt in seawater, sugar in tea, nutrients in blood, all dissolve thanks to water's abilities. This is why it is called the universal solvent, though perhaps a more accurate description would be the universal matchmaker, always bringing together molecules that might otherwise never meet. Its solvent power makes life possible at the cellular level. Proteins fold into their functional shapes because water surrounds them in specific ways. DNA maintains its famous double helix thanks to hydrogen bonds both within the molecule and with the water around it. Even the simplest reactions in metabolism rely on water to shuttle atoms back and forth. Far from being a passive backdrop, water is an active participant in the drama of biochemistry. Water's mischief extends into the sky as well. As it evaporates, it carries away heat, making sweat an effective cooling system. When it condenses, it releases that heat back into the atmosphere, fueling clouds and storms. Hurricanes, monsoons, and gentle rains alike owe their power to water's ability to change phase and transfer energy. It is the quiet engine that drives much of the weather. One might think that all this rule-breaking would make water unique only to Earth, but astronomers are increasingly finding it across the cosmos. In icy moons, in interstellar clouds, even in the thin atmospheres of distant exoplanets, water molecules are detected again and again. Yet no matter where they are found, they carry the same peculiarities, the same bent structure and polar bonds. This universality suggests that if life exists elsewhere, it may well depend on water's chemistry just as we do. What is remarkable is that we often overlook just how peculiar our daily encounters with water truly are. We sip it without realizing that it should not be liquid at room temperature. We watch ice cubes float in a glass, without marveling that this behavior defies the expectations of most materials. We see insects skating on ponds without pausing to consider the invisible bonds beneath their feet. Water disguises its strangeness in plain sight, hiding its quirks under a cloak of familiarity. Scientists have studied water for centuries, and yet it still holds mysteries. Some of its properties at extreme temperatures and pressures remain puzzling. Computer models struggle to capture all of its behavior precisely. It is as if water enjoys keeping a few secrets, reminding us that even the most common substance can surprise. Perhaps the best way to appreciate water is to imagine a world without its peculiar chemistry. A planet where ice sinks, oceans freeze solid, proteins unravel, and storms never gather would be lifeless. The rules that water breaks are the rules that make life possible. Its quirks are not accidents but the very foundation of complexity, resilience, and beauty. Water may look like an obedient liquid, but in truth it is a cosmic prankster with a serious purpose. It bends the rules of density, temperature, and chemistry, and because of that, rivers flow, clouds form, cells function, and life endures. To lift a glass of water is to hold in your hand not just a refreshment, but one of nature's greatest oddities, a simple molecule with the power to shape a world. In the beginning, life was small, fragile, and entirely aquatic. For hundreds of millions of years, the oceans were not just home to living things, they were the only place life existed. From microscopic cells adrift in ancient seas to the spectacular bloom of creatures in the Cambrian period, water cradled every stage of biology's earlier steps. It was a vast, dynamic nursery, and without its sheltering embrace, evolution might never have found its footing. The earliest life forms were single-celled organisms, tiny entities that floated in watery environments over 3.5 billion years ago. They left behind traces in the form of stromatolites, layered structures built by microbial mats that trapped and bound sediments. Some stromatolites still exist today in shallow lagoons, a living window into an ancient past. These organisms relied on water not only for stability, but also for the chemistry of survival. Water dissolved nutrients, carried them into cells, and provided the medium for reactions that powered metabolism. Without liquid water, such primitive organisms would have had no stage on which to live. One of the most revolutionary steps in this early history was photosynthesis. Cyanobacteria, often called blue-green algae, learned to harness sunlight, using water as the source of electrons to build sugars. In the process, they released oxygen as waste. This oxygen would eventually accumulate in the atmosphere during the Great Oxidation event, about 2.5 billion years ago, fundamentally altering Earth's chemistry. The irony is that what was once just a byproduct of microbial metabolism became the essential gas for complex life. Water was not only the environment, but also the key ingredient in this transformation. As splitting water molecules powered the rise of oxygenic photosynthesis. As life diversified, the oceans became increasingly complex. Cells began working together, forming colonies and eventually multicellular organisms. This leap allowed specialization. Some cells handled movement, others digestion, others reproduction. The oceans grew crowded with forms more varied than the simple microbes that had dominated for billions of years. The groundwork was being laid for the explosion of diversity that would arrive in the Cambrian. The Cambrian period, beginning around 540 million years ago, is often described as evolution's Big Bang. Within a geologically short span of time, an astonishing array of creatures appeared in the seas. Trilobites scuttled across the seafloor with armoured bodies and compound eyes. Worm-like burrowers tunneled through sediments, churning and aerating the seabed. Sponges filtered water for nutrients, while early predators such as Anomalocaris swam with grasping appendages and circular mouths lined with teeth. Almost every major animal group alive today can trace its origins back to this burst of creativity in the Cambrian seas. Water was central to this flourishing. Buoyancy allowed creatures to grow larger than they could have managed on land, since their weight was supported by the medium around them. Currents distributed nutrients and oxygen, sustaining ecosystems from shallow reefs to deeper basins. The very act of moving through water, whether by swimming, drifting, or crawling, drove the evolution of muscles, skeletons, and sensory systems. The challenge of navigating a three-dimensional environment spurred innovation after innovation. The chemistry of seawater also played a part. Dissolved minerals provided the raw material for shells and skeletons. Calcium carbonate, readily available in the oceans, was fashioned into protective armour by trilobites, brachiopods, and corals. The evolution of hard parts not only gave animals defence against predators, but also left behind fossils that preserved their forms in exquisite detail. Our understanding of the Cambrian explosion comes largely from these mineralized remains, testimony to how water's chemistry shaped biology and preserved its record. The Cambrian seas were not static aquariums, but dynamic arenas where ecosystems interacted and evolved. Predation intensified, driving arms races between hunters and prey. Some animals developed spines, others grew faster or more agile, and still others learned to burrow for protection. Each adaptation was tested in the watery environment, where the rules of survival were written by currents, light, and chemistry. Even after the Cambrian, the oceans remained the heart of evolution for hundreds of millions of years. Fish emerged, first with simple cartilaginous skeletons, then with bony structures that gave them more strength and versatility. Fins evolved, eyes sharpened, and jaws appeared, opening up entirely new possibilities for feeding. Coral reefs blossomed as hubs of biodiversity, while vast schools of plankton fed the food chains that extended all the way to the largest marine reptiles and mammals that would come much later. Through it all, water provided stability. It buffered organisms from dramatic temperature swings, unlike the more variable conditions on land. It shielded fragile tissues from the harsh ultraviolet radiation that bathed the surface world before the ozone layer thickened. It supplied the medium for gases and nutrients to diffuse directly into cells. Life in the oceans was not easy, but it was possible, and for billions of years, it was the only possible stage. The eventual move onto land was one of the most daring experiments in evolutionary history, but it was only possible because life had spent eons perfecting itself in water. Limbs strong enough to bear weight, skin tough enough to resist drying out, lungs efficient enough to breathe air. All of these adaptations were honed in aquatic ancestors before they were tested on land. Even today, the fingerprints of this watery past remain. Our blood is salty, echoing the composition of ancient seas. The embryos of vertebrates develop in fluid-filled sacs, tiny oceans carried within us. Life carries its birthplace wherever it goes. When we look back on the story of early life, it is impossible to separate it from water. The first cells floated in it, the first multicellular organisms were shaped by it, and the great Cambrian explosion unfolded entirely within it. Water was cradle, catalyst, and constant companion. The oceans that stretched across the Cambrian Earth were teeming with forms both familiar and alien, but all shared one thing in common. They were children of water. From single cells that learned to harness sunlight to trilobites marching in armoured lines across the seafloor, every step in evolution's early dance was choreographed by the sea. Long before there were forests or deserts, long before there were birds in the sky or mammals on the land, there were oceans filled with experiments in living, all of them carried by water's embrace. In this sense, water was not just the backdrop of early life, but its co-author, guiding, protecting, and challenging it until the great leap onto land could be made. The story of life's beginning is, at its core, the story of water itself, a tale of chemistry transformed into biology, played out in the endless rhythms of the sea. When people picture water on Earth, the mind usually drifts to oceans, rolling waves, crashing surf, or the vast blue that dominates maps and photographs from space. Yet almost all of that water, over 97% of it, is salty and undrinkable without significant effort. Fresh water, the kind we can sip, irrigate crops with, or pipe into cities, makes up less than 3% of Earth's total supply. Even then, most of that small fraction is locked away in glaciers, ice caps, or hidden deep underground. The water that flows freely in rivers and fills lakes, the part that sustains billions of people, animals, and ecosystems, amounts to less than 1% of all freshwater on Earth. In the grand tally of planetary resources, liquid freshwater is astonishingly rare. Rivers are perhaps the most familiar form of freshwater, winding through landscapes, carrying rainfall and meltwater from mountains to seas. They are dynamic systems, constantly shifting their channels, eroding banks and depositing fertile soil. Rivers do more than quench thirst. They have sculpted civilizations. The Nile, the Tigris and Euphrates, the Indus and the Yellow River were the cradles of agriculture and early urban life. They provided not only water but transport, food and a natural calendar through floods and seasonal flows. Yet rivers are only a thread of the freshwater story, a thin ribbon compared to the vast reservoir of the oceans. Lakes, by contrast, act as basins of stability. They store enormous quantities of fresh water, some for mere decades and others for millions of years. The Great Lakes of North America hold about 1/5 of the world's surface freshwater, an immense inland sea system created by retreating glaciers. Lake Baikal in Siberia, the deepest and oldest lake on Earth, contains more freshwater than any other single lake, holding roughly 20% of all unfrozen surface water. Each of these lakes is not just a collection of water, but an ecosystem, home to unique species that evolved in isolation. Hidden beneath our feet are aquifers, subterranean reservoirs that store water in porous rock and soil. These underground reserves dwarf the accessible water on the surface. For thousands of years, humans have tapped them with wells, sometimes shallow and simple, other times vast and industrial, Aquifers supply drinking water for billions and irrigate fields that feed the world. Yet they are not limitless. In some regions, aquifers recharge slowly, depending on rainfall seeping into the ground. When pumping exceeds replenishment, the water table falls and wells run dry. This overuse has become a pressing challenge in places such as the Ogallala Aquifer in the central United States or northern India's groundwater systems. The scarcity of fresh water has shaped human history in ways both creative and desperate. Ancient societies built canals and aqueducts to bring water to growing populations. The Romans constructed aqueducts so precise and durable that many still stand today. In arid regions, ingenious underground channels called qanats carried groundwater from hills to fields and villages. Entire cultures rose and fell depending on their ability to manage limited supplies. Droughts have toppled kingdoms, forced migrations, and sparked conflicts, while abundant rivers and lakes have supported flourishing trade and growth. Even today, water scarcity remains a defining issue. Around the world, billions of people lack consistent access to safe drinking water. Climate change adds to the pressure. As glaciers retreat, rainfall patterns shift, and droughts intensify. In some regions, competition for water between agriculture, industry, and households grows fiercer each year. Cities like Cape Town have faced near-day zero events, where reservoirs came perilously close to running dry. The contrast between abundance in some regions and scarcity in others highlights just how unevenly Earth's precious fresh water is distributed. One reason fresh water is so precious is that it is constantly in motion. Unlike oil or coal, it is renewable, but it is also elusive. Rain may drench one valley while leaving another parched. Rivers can flood with destructive force one season and shrink to a trickle the next. Aquifers can store water for centuries, yet once depleted they may take equally long to refill. The cycle ensures that fresh water is always on the move, but it also means that managing it requires patience and foresight. The chemistry of fresh water adds another layer of importance. Unlike seawater, it can be consumed directly, though often not without some purification. Its lack of salts makes it ideal for agriculture, preventing the accumulation of minerals that can ruin soils. Animals evolve to drink it, plants to thrive on it. In short, the biology of Earth depends on this tiny minority of water, as though all of life has placed its bets on a small, precious share of the global supply. Freshwater ecosystems themselves are remarkably diverse. Rivers and lakes are home to amphibians, fish, insects, and plants, adapted to unique conditions. A single river can host salmon that migrate thousands of kilometers, while a small lake may shelter species found nowhere else. Wetlands, often overlooked, act as natural sponges, storing floodwaters and slowly releasing them, while also filtering pollutants and providing habitat for countless birds. The richness of these systems makes the scarcity of fresh water all the more poignant. Throughout history, societies have responded to scarcity with ingenuity but also with conflict. Wars have been fought over access to rivers, and treaties have been signed to share waters between nations. Modern technology allows desalination of seawater, turning salt water into fresh water, but it is energy-intensive and expensive. Dams and reservoirs can store water, yet they disrupt ecosystems and displace communities. The search for solutions is ongoing, balancing human needs with the health of the planet's freshwater systems. One striking example of scarcity's impact is the Aral Sea, once the fourth largest lake in the world. Over the 20th century, rivers feeding it were diverted for irrigation. Within decades, the lake shrank to a fraction of its size, devastating fisheries, altering local climates, and leaving behind a desert of salt and dust. It is a cautionary tale of how fragile freshwater resources can be when demand outpaces supply. Despite challenges, there is also resilience. Restoration projects have brought parts of the Aral Sea back to life. Rivers once polluted beyond recognition have been cleaned and revived. communities are increasingly turning to conservation, recycling, and smarter irrigation to stretch supplies further. The story of freshwater is not only one of scarcity, but also of adaptation and recovery. When viewed against the immensity of Earth's oceans, freshwater may seem insignificant. Yet it is this rare fraction that shapes the course of human history, feeds crops, quenches thirst, and sustains the most delicate of ecosystems. Every river, every lake, every aquifer is part of a thin but vital thread woven through the fabric of life. The next time you pour a glass of water, consider that it comes from a supply so limited that it could fit in the tiniest corner of the planetary ledger. Out of all the water on Earth, only a minuscule sliver is fresh and liquid, accessible for drinking, farming, and survival. That rarity makes it precious beyond measure, a clear reminder that sometimes the smallest share of a resource can carry the greatest weight in sustaining a world. Civilization has always been drawn to water. Long before skyscrapers or satellites, people gathered where rivers flowed. They provided drinking water and fish, of course, but their influence stretched far beyond survival. Rivers offered fertile land, natural highways, and a steady rhythm that made planning possible. They were the lifeblood of the earliest cities, the quiet but constant force shaping the rise of human culture. Consider the Nile, often called the gift of Egypt. Without it, the surrounding landscape would have been an unforgiving desert. With it, Egypt became one of the most enduring civilizations of the ancient world. Each year the river flooded, spreading nutrient-rich silt across its banks. This natural fertilization allowed farmers to grow wheat, barley, and flax in abundance. The predictability of the Nile's flood was unlike that of most rivers, so regular it was almost like a clock. This reliability not only supported agriculture but also gave Egyptians a sense of cosmic order. They built calendars around the flood, aligned their myths with its cycles, and even structured their political authority around managing its waters. In many ways, the pharaoh's legitimacy rested on the river itself, for to control the Nile was to control life. The Nile was more than a farmhand. It was a highway linking Upper and Lower Egypt, carrying boats laden with grain, stone, and goods. Its steady northward current was balanced by prevailing southward winds, making two-way travel remarkably efficient. Traders, soldiers, priests, and messengers all moved along this watery road. Temples and monuments were built close to its banks, so that the river became both a practical and spiritual artery. To this day, Egyptian identity remains inseparable from the Nile's flow. Further east between the Tigris and Euphrates lay Mesopotamia, whose very name means the land between rivers. Here too, fertile soil and water allowed agriculture to thrive. Unlike the Nile, these rivers were less predictable, prone to sudden floods that could destroy crops as easily as they nurtured them. To manage this volatility, Mesopotamian societies developed irrigation systems, canals, levees, and reservoirs that redistributed water and tamed its force. These engineering feats required cooperation, which in turn gave rise to organized government. The Sumerians, Babylonians, and Assyrians built not just farms, but cities and empires, with rivers at their heart. The rivers of Mesopotamia were also thoroughfares of trade. They connected inland regions to the Persian Gulf, linking distant peoples through commerce in grain, textiles, and metals. With trade came writing. The earliest cuneiform tablets often recorded transactions of grain and livestock, all dependent on the river's generosity. Even law was tied to water. The famous Code of Hammurabi included rules about irrigation and canal maintenance, acknowledging that in a dry land, water was the ultimate shared responsibility. To the east in the Indian subcontinent, the Indus River supported another cradle of civilization. The Indus Valley civilization flourished around 4,000 years ago, building carefully planned cities such as Mohenjo-Daro and Harappa. The river's floods deposited rich soils that supported farming, while its waters nourished crops like wheat, barley, and cotton. The people of the Indus engineered remarkable drainage and sewage systems, suggesting that water management was central to their urban planning. Though much about their culture remains mysterious, the Indus itself is undeniable evidence of their prosperity. It linked communities, allowed for trade both inland and with the Arabian Sea, and provided the agricultural stability upon which their society rested. China, too, was shaped by its rivers. The Yellow River, often called the cradle of Chinese civilization, deposited loess, a fine, fertile soil that made farming possible on a vast scale. Yet the river was also capricious, earning the nickname China's Sorrow because of its devastating floods. Dynasties rose and fell in part on their ability to manage the Yellow River's waters through levees and canals. Rice cultivation along the Yangtze later transformed diets and economies, supporting dense populations and fueling cultural growth. Both rivers became not just sources of food, but symbols of identity, woven into literature, art, and political authority. Across these regions, rivers were not only providers of food, but also shapers of culture and imagination. Flood myths, often involving waters that cleansed or reshaped the world, appear in many traditions. The biblical story of Noah, the Mesopotamian tale of Utnapishtim, and the Hindu story of Manu all reflect humanity's deep respect and fear of the power of rivers. They were at once gentle givers and unpredictable destroyers, gods in their own right. Agriculture, perhaps the most important step in human history, would not have been possible without rivers. Fields watered by rainfall alone often fail, but rivers create certainty. They allow irrigation, turning dry soil into fertile farmland and sustaining crops even during droughts. With food surpluses, populations grew. With larger populations came specialization, artisans, traders, priests and rulers. Cities blossomed, then states, then empires. All of it flowed from the rivers. Trade followed the waterways. Before roads and railways, rivers were the fastest and easiest means of transporting goods. Grain, stone, timber, and precious metals could all move in bulk by boat. In this sense, rivers were the first international highways, carrying not only products but ideas. Technologies, languages, and religions spread along river valleys, mingling cultures just as waters mingled at their deltas. Rivers also demanded respect and ingenuity. Floods destroyed cities as often as they nourished them. Managing water required mathematics, engineering, and cooperation on a grand scale. Dams, levees, and canals became hallmarks of early civilization, feats that demonstrated collective power and foresight. The societies that mastered these tools prospered, those that failed often crumbled. Yet despite differences in geography, climate, and culture, the story was remarkably similar across continents. Wherever a great river flowed, a civilization followed. The Nile, the Tigris and Euphrates, the Indus, the Yellow and Yangtze, each gave rise to cities, trade, and culture. Even later civilizations, from the Romans along the Tiber to the Mayans near rivers in Central America, continued this pattern. Water was the thread binding humanity's rise together. The reliance on rivers also shaped our psychology. To ancient peoples, the river was not simply a resource but a presence, alive, powerful, and worthy of reverence. Ceremonies honoured it, myths explained its moods, and rulers built their legitimacy on its flow. To this day, rivers remain symbols of life, renewal, and passage, flowing through literature and art as much as through valleys and plains. When we look back at the birth of civilization, it is clear that water was not just a backdrop, but the stage itself. Rivers gave humans more than sustenance. They gave them structure, opportunity, and imagination. They carved out fertile soils, offered routes for trade, and inspired cooperation on scales large enough to build cities. The history of civilization is, in many ways, a history of rivers. Every time a river swells in spring carrying snowmelt to fields, it echoes the ancient rhythm that nurtured the first farmers. Every boat that drifts down a waterway recalls the traders who once carried grain and pottery between cities, and every flood that threatens to sweep away a town is a reminder that rivers remain as powerful and unpredictable as they were thousands of years ago. Civilizations rose by the riverbanks, flourished with their waters, and sometimes fell when the floods turned against them. To this day, our lives are entwined with rivers, whether we live beside them or depend on the crops and goods they sustain. The story of humanity is inseparable from these flowing arteries of earth, for it was rivers that first taught us how to live together, to farm, to trade, and to dream. Water has always been more than a physical necessity. From the earliest days of human culture, people looked at rivers, springs, and seas and saw something greater, symbols of purity, renewal, danger, and even the divine. Across civilizations, water has been revered, feared, and celebrated. It is the one substance that crosses boundaries between the physical and the spiritual, the practical and the poetic. In India, the Ganges River is perhaps the most famous example of sacred water. For Hindus, the Ganges is not just a river, but a goddess, Ganga, who descended from heaven to purify the earth. Pilgrims travel from across the subcontinent to bathe in its waters, believing that immersion can wash away sins and bring spiritual liberation. Ashes of the dead are scattered into its current, carrying souls toward salvation. The river is both a geographical and spiritual lifeline, embodying renewal in every ripple. Despite pollution and modern pressures, its sanctity endures, a testament to how powerfully water can hold meaning across millennia. Other cultures too sanctified their rivers. The ancient Egyptians saw the Nile not only as a source of food but as a divine gift. Its annual flood was celebrated in rituals, understood as the breath of gods renewing the land. In Mesopotamia, rivers were both feared and worshipped. The unpredictable floods of the Tigris and Euphrates inspired myths of cosmic deluges and gods who controlled the waters. Rituals to appease these deities were as essential to survival as irrigation canals. Water, in these societies, was the very expression of divine will. Beyond rivers, springs and wells carried spiritual weight. In Greece, sacred springs were said to be inhabited by nymphs, minor deities who embodied nature's vitality. The oracle at Delphi spoke beside the Castalian spring, whose waters were believed to inspire prophecy. Celtic cultures across Europe venerated wells, tossing offerings of coins, jewellery and weapons into their depths. These acts recognized springs as portals between the human and divine, places where the veil of the world thinned. Bathing rituals also carried symbolic force. In Judaism, the mikveh, a ritual bath, is used for purification, marking moments of spiritual transition. Christianity adopted water as the central element in baptism, the symbolic washing away of sin and the beginning of new life. In Islam, ablution with water before prayer emphasizes physical and spiritual cleanliness, connecting worship with purity. Across faiths, water is the universal medium for renewal, its ability to cleanse the body mirrored in its ability to cleanse the soul. In some traditions, vast bodies of water symbolized chaos and the unknown. The sea, with its unpredictable storms and infinite horizon, often embodied danger and mystery. In Mesopotamian mythology, the primordial sea goddess Tiamat represented the chaos from which the world was formed. In the Hebrew Bible, the deep waters of creation were formless until ordered by divine command. In Norse mythology, the world emerged from the meeting of fiery and icy realms, their melting waters giving birth to the first beings. Again and again, water is depicted not only as life-giving, but as the raw, untamed substance from which all creation flows. The symbolic power of water is not always gentle. Flood myths are nearly universal, reflecting humanity's experience of devastating inundations. The story of Noah in the Hebrew Bible, the Epic of Gilgamesh from Mesopotamia, and flood legends among Native American, Chinese and Mesoamerican cultures all tell of waters that cover the earth, destroying civilizations but also offering a chance for renewal. These tales cast water as both destroyer and creator, capable of erasing worlds and giving birth to new ones. For indigenous peoples, water has often been understood as kin, a living presence with whom humans share reciprocal relationships. Many North American indigenous traditions describe water as a relative rather than a resource, honoured in ceremonies and songs. The Maori of New Zealand see rivers as ancestors, leading to modern legal recognition of some rivers as living entities with rights of their own. Such views emphasise not just reverence but responsibility, a recognition that water and life are inseparably linked. Even in secular contexts, water has retained its symbolic weight. Cities have built fountains not only to distribute drinking water, but to represent abundance and beauty. In Renaissance gardens, waterworks symbolised human mastery over nature, while also delighting visitors with displays of power and elegance. In literature, poets and novelists have long turned to rivers as metaphors for time, love, and memory. "You cannot step into the same river twice," wrote the Greek philosopher Heraclitus, capturing in a single phrase the endless motion and change that water represents. The act of pilgrimage often follows rivers or seeks sacred springs. Walking beside water has been a journey toward clarity for countless generations, whether it is a traveller dipping their hands into the Jordan River, a Buddhist monk meditating by a mountain stream, or a modern hiker finding peace beside a waterfall. The sense of connection to something larger than oneself is nearly universal. The endurance of these practices across cultures suggests that water taps into something fundamental in the human psyche. It reflects us, literally and symbolically. It can be calm or turbulent, generous or unforgiving. It gives life, but also takes it. It is at once ordinary and otherworldly, the glass of water on your table, and the river in which a civilization sees the face of its gods. The sacredness of water also reveals how societies made sense of its essential role. Without science to explain rainfall, floods, and springs, people turn to myth and ritual. But even with science now explaining these processes, the symbolic resonance of water has not disappeared. Baptisms continue, offerings are still made at springs, and rivers remain woven into the spiritual fabric of communities. When people stand on a riverbank or immerse themselves in a sacred bath, they are engaging with water in ways that go beyond survival. They are acknowledging its power to renew, to cleanse, to carry away the old and deliver the new. Whether seen as goddess, ancestor, or symbol, water has always meant more than molecules. It is meaning itself flowing across the boundaries of culture, time, and belief. Water is practical, yes, but it is also profoundly symbolic. It has been revered as a goddess, feared as a flood, honoured as a purifier, and trusted as a path to the divine. In every culture, at every time, people have turned to water not just for life, but for meaning. And in return, water has flowed through human imagination as endlessly as it flows through rivers and seas. For most of human history, water was not just a mystery of survival, but also a puzzle of understanding. People could see rivers flowing, tides rising, rain falling, and fog clinging to valleys. Yet the mechanics behind these phenomena were elusive. To watch water was to see constant change, liquid to vapour, ice to melt, clouds to rain, and each transformation begged for explanation. The story of science's encounter with water is in many ways the story of curiosity itself, a journey from ancient speculation to the precise hydrology of today. The earliest recorded attempts to explain water's behaviour came from the ancient Greeks. Thales of Miletus, one of the first philosophers, declared that water was the fundamental substance of all things. To him, everything could be traced back to water, the prime element. It was not a bad guess, considering how essential water appeared in everyday life. Though his idea was more philosophy than chemistry, it set the tone. Water was not just necessary, it was central to the structure of the world. Later Greek thinkers offered refinements. Aristotle described water as one of the four classical elements, alongside earth, air and fire. He associated it with cold and wet qualities, fitting neatly into his broader framework of natural philosophy. For centuries, these elemental ideas dominated thought, framing water as a basic building block of reality rather than a compound made of atoms. Still, Aristotle observed keenly, noting processes like evaporation and condensation, even if the mechanisms eluded him. His descriptions of how vapour rises from the sea to form clouds were impressively close to modern understanding, considering the lack of scientific tools at his disposal. Other cultures contributed insights as well. In China, early scholars studied rainfall, floods, and irrigation with practical precision. Ancient Indian texts described rain cycles and the importance of monsoons. Islamic scholars in the medieval world advanced ideas about evaporation and the water cycle. Al-Kindi and later Al-Biruni discussed the transformation of water into vapour, while Ibn Sina, known in the West as Avicenna, wrote about condensation and precipitation. Their works preserved and expanded knowledge at a time when much of Europe relied on classical texts alone. In medieval Europe, water remained an enigma. Rivers were dammed, canals built, wells dug, yet few understood where rain came from or why tides rose and fell. Some believed tides were caused by great underwater breathing of the earth itself. Others linked them vaguely to the moon without understanding the gravitational mechanics. It took centuries for observations to solidify into theories that could withstand scrutiny. The Renaissance brought a shift. As natural philosophy evolved into science, thinkers began to test and measure water rather than simply speculate. Leonardo da Vinci sketched vortices, currents, and the eddies of rivers with astonishing detail. He called water the vehicle of nature, and studied it with the same curiosity he applied to anatomy and flight. Though many of his ideas remained unpublished during his lifetime, his notebooks reveal a mind captivated by the motion of water in all its forms. By the 17th century, the scientific revolution was in full flow, and water became a subject of systematic inquiry. Evangelista Torricelli invented the barometer in 1643, showing that air pressure could support a column of mercury. This discovery illuminated the role of pressure in weather and hinted at how water rose through pumps and wells. Soon after, Blaise Pascal expanded on these ideas, laying foundations for hydrodynamics and hydrostatics. Rainfall, too, came under study. For centuries, people assumed rivers were fed by subterranean sources, perhaps vast underground oceans. It seemed implausible that rainfall alone could supply so much water. In the 17th century, French scientist Pierre Perrault carefully measured rainfall over the Seine River basin. To the surprise of many, he showed that precipitation alone was more than sufficient to explain the river's flow. His colleague Edmé Mariotte confirmed these results, and together they helped establish the modern understanding of the water cycle: evaporation, condensation, precipitation, and runoff working in a continuous loop. Meanwhile, tides finally yielded their secrets. Johannes Kepler had suggested that the moon's attraction might be irresponsible, an idea that Isaac Newton later formalized with his law of universal gravitation. In his Principia of 1687, Newton demonstrated mathematically how the moon and the sun tug on Earth's oceans, creating the regular rise and fall of tides. What had once been mysterious breathing of the planet was now explained with elegant physics. The 18th and 19th centuries brought new precision. Scientists such as Daniel Bernoulli studied fluid dynamics, laying out principles that describe how water flows through pipes and rivers. His famous Bernoulli's principle, though often applied to air and flight, is rooted in the study of fluid motion. Later, in the 19th century, William Thomson, better known as Lord Kelvin, and others worked to understand ocean circulation and tidal patterns, using mathematics and careful observation to chart the pulse of the seas. Hydrology emerged as a formal science in the modern era. Researchers studied groundwater, aquifers, and how rainfall infiltrates soils. Engineers applied these principles to build dams, canals, and reservoirs, shaping entire landscapes. The science of meteorology, deeply tied to water in the form of clouds, rain and humidity, grew rapidly in the 19th and 20th centuries. Satellites in the modern age now allow us to watch water vapour swirl across the atmosphere, track storms as they form, and even measure soil moisture from space. One of the great milestones in the study of water came with the discovery of its molecular nature. In the late 18th century, Antoine Lavoisier and Henry Cavendish identified water not as an element, but as a compound of hydrogen and oxygen. Lavoisier, through careful experiments, showed that water could be broken down into these gases and recombined again. This revelation shattered the old elemental model and confirmed the emerging atomic theory of matter. A substance so common, once thought indivisible, was revealed to have structure and recipe. The modern science of water spans disciplines. Chemists investigate its hydrogen bonds and peculiar behaviours. Physicists model how droplets form, how ice crystals grow, and how turbulence shapes clouds. Biologists study water's role in ecosystems, from rivers nourishing forests to the moisture cycles of rainforests themselves. Hydrologists map aquifers and model river basins. Climate scientists watch oceans absorb heat and track how melting glaciers alter sea levels. In every corner of science, water continues to be central, still as fascinating as when Thales declared it the origin of all things. What makes the history of water in science particularly charming is how often it has surprised us. Assumptions about underground seas, about the immutability of elements, about the mechanics of tides, all had to be overturned. Again and again, water demonstrated that it was not only essential but also enigmatic. It looked simple, yet it challenged some of the brightest minds in history. Even now, mysteries remain. The precise behaviour of water at very small scales, its role in quantum systems, and its odd properties at extreme pressures and temperatures are subjects of ongoing research. The molecule that seemed so ordinary continues to puzzle, offering new questions to each generation of scientists. From ancient philosophers to modern satellites, the pursuit of water's secrets has been a mirror of human curiosity. Every time we solved one piece of the puzzle, water revealed another layer of complexity. It has been both laboratory and teacher, forcing us to refine our methods, to measure more carefully, to think more deeply. The science of water is not a closed book, but a living field, flowing as steadily as the rivers it seeks to understand. In the end, water has always been more than what fills rivers and falls from clouds. It has been the spark for ideas, the test of theories, and the measure of our scientific progress. To trace the history of water in science is to trace the growth of human understanding itself, a story still unfinished, still moving, just like water. In the modern world, water has become both more ordinary and more extraordinary. It runs invisibly through pipes into kitchens and bathrooms, so familiar that its arrival feels automatic. At the same time, it has been harnessed to build vast dams, power industries, irrigate entire continents, and even spark international tensions. No longer just a gift of nature, water is now something humans attempt to engineer, regulate, and at times fight over. Industry has made water into a silent partner in progress. Factories use it to cool machines, clean materials, and process goods. Power plants, whether fueled by coal, gas, or nuclear reactions, rely on it to convert heat into steam and turn turbines. Steel, paper, textiles, electronics all depend on steady water supplies. Even products that seem dry, like microchips or denim, carry enormous water footprints hidden in their manufacture. In the modern economy, water is as essential as electricity, though it is often less visible because it flows quietly behind the scenes. Water has also been turned into power directly. Hydroelectric dams capture the force of rivers, transforming gravity-fed flows into electricity. The Hoover Dam, completed in the 1930s, not only provided energy, but also symbolized human ability to tame nature. The Three Gorges Dam in China, one of the largest in the world, spans the Yangtze River and generates more electricity than many countries consume. Dams like these provide renewable power, control floods, and store water for irrigation, but they also reshape ecosystems, alter sediment flows, and displace millions of people. Each reservoir reflects a balance between benefit and cost, between human ambition and environmental consequence. Beyond electricity, dams and canals have redrawn entire maps of water distribution. Irrigation networks stretch across deserts, feeding fields that would never have grown crops otherwise. The Aswan High Dam in Egypt controls the Nile's floods, allowing year-round agriculture. Canals in South Asia channel Himalayan meltwater to feed millions. In California, aqueducts carry water hundreds of kilometers from snowy mountains to sprawling cities and farmland. These feats of engineering have made modern civilization possible, but they also illustrate a profound truth. Water does not naturally flow where humans always want it, so we move it ourselves. This moving of water has consequences. When rivers are dammed or diverted, ecosystems downstream can wither. The Aral Sea, once one of the largest lakes in the world, has nearly vanished after rivers that fed it were redirected for irrigation. In other places, reservoirs trap sediment that would have nourished deltas and coastlines, leaving them vulnerable to erosion and rising seas. Modern control of water often solves one problem while creating another, a reminder that water's cycles are not easily bent to human plans. Water is also a source of cooperation, as nations that share rivers must find ways to share resources. The Mekong River winds through 6 countries in Southeast Asia, each dependent on its flow for food and energy. The Nile connects 11 nations, from its sources in East Africa to its mouth in Egypt. Agreements, treaties, and international organizations attempt to manage these shared waters, but tensions often simmer beneath the surface. Water, though renewable, is not evenly distributed, and its scarcity can bring communities together or drive them apart. Conflicts over water are not only international. Within nations, competing demands between agriculture, industry, and households create friction. Agriculture alone consumes about 70% of freshwater withdrawals globally, much of it lost to inefficient irrigation. Cities compete with farmers, industries with ecosystems. A reservoir that feeds crops may also supply drinking water to millions. Deciding who gets how much is as much a political question as a hydrological one. Yet water is also a force for unity. Modern cities could not function without vast water systems that integrate reservoirs, pipelines, treatment plants, and sewage networks. When these systems work, they're nearly invisible, a silent miracle of engineering that allows millions to share the same resource without chaos. When they fail, as in cases of drought or contamination, societies are reminded of their dependence. Clean water is no longer a given, but a triumph of constant management. The modern global water cycle is no longer entirely natural. Human activity has altered it at every scale. Deforestation changes rainfall patterns, as fewer trees mean less moisture evaporating into the atmosphere. Cities, with their concrete and asphalt, channel rain into sewers instead of allowing it to seep into aquifers. Dams trap rivers. Irrigation evaporates huge amounts of water, and climate change intensifies droughts and floods alike. Even groundwater, once thought inexhaustible, is being drained faster than it can be replenished. Aquifers in parts of India, China, and the United States are dropping rapidly, their ancient stores of water vanishing in mere decades. Pollution adds another layer of challenge. Industrial waste, agricultural runoff, and untreated sewage contaminate rivers and lakes. Fertilizers create dead zones in coastal waters where oxygen is depleted and marine life struggles to survive. Plastic waste floats across oceans in gyres larger than countries. For billions of people, the issue is not just the quantity of water, but the quality, as clean drinking water remains out of reach. Despite these challenges, water remains a wellspring of ingenuity. Engineers develop new desalination plants to convert seawater into drinking water. Scientists explore fog harvesting nets in deserts and new technologies for recycling wastewater. farmers experiment with drip irrigation to save every drop, while urban planners design green roofs and permeable pavements to capture rain. Humanity continues to invent ways to stretch and share this most basic resource. Yet for all the modern interventions, water still resists complete control. Floods overwhelm levees, droughts empty reservoirs, and storms remind us that water obeys natural laws, not political ones. It remains, as it has always been, both a source of power and a reminder of limits. Our efforts to master it reveal not only our ambition, but also our dependence. Perhaps what is most striking about water in the modern world is how it binds together the global community. A factory in one country consumes water embedded in its products, which are shipped across oceans to another. A drought in a grain-producing region ripples through international markets, affecting bread prices continents away. A river dammed in one nation changes ecosystems in another. Water has become not only a local concern, but a global one, woven through trade, politics, and climate. From the tap in a kitchen to the vast sweep of a dammed river, the story of water today is one of immense possibility and immense challenge. It is a reminder that even the most ordinary glass is part of a vast and intricate system that spans the globe. In trying to control water, humanity has revealed just how much it depends on it. And in a world of growing populations and changing climates, the question is no longer whether water will shape our future, but how wisely we will shape our relationship with water. Glaciers are among Earth's most imposing features, yet they are also among the most delicate. These rivers of ice form when snowfall accumulates over centuries, compacting into dense ice that begins to flow under its own immense weight. To stand at the edge of one is to feel the presence of time itself. They are slow but relentless, carving valleys, grinding mountains into dust, and feeding rivers that sustain entire ecosystems. At their height, during the last ice age, glaciers covered much of the northern hemisphere, their weight pressing down continents and their reach reshaping coastlines. Even today, Antarctica and Greenland hold the majority of Earth's fresh water, locked in frozen sheets several kilometers thick. What makes glaciers so extraordinary is their dual nature. They are both static and dynamic. From a distance they look like frozen monuments, but closer inspection reveals crevasses opening and closing, ice flowing like a viscous liquid, and chunks calving dramatically into the sea. They move slowly, sometimes only a few centimeters a day, yet over centuries they can carve landscapes on a continental scale. Fjords in Norway, the Great Lakes of North America, and the U-shaped valleys of the Alps all bear witness to glacial sculpting. Water in its solid form has shaped more of Earth's geography than many forces we consider far more violent. These glaciers are not just frozen landscapes, they are reservoirs of fresh water. If the ice sheets of Greenland and Antarctica were to melt entirely, global sea levels would rise by more than 60 meters. Even small shifts in glacial mass have profound consequences for coastlines and communities. This makes glaciers a barometer of climate, sensitive indicators of warming. They shrink when the planet heats, grow when it cools, and in their advance and retreat they write the story of Earth's changing climate across deep time. Yet Earth is only one stage for frozen water. Across the solar system, ice appears again and again, shaping moons, planets, and dwarf planets into strange and beautiful worlds. One of the most intriguing is Europa, a moon of Jupiter. At first glance, Europa looks like a ball of ice, its surface etched with cracks and ridges. These patterns suggest movement beneath, as if the shell of ice is floating on an ocean of liquid water. Evidence from spacecraft indicates that this hidden ocean may be one of the largest in the solar system, kept warm by the tidal flexing of Europa's interior as Jupiter's gravity pulls and squeezes it. If confirmed, Europa would be a world with more liquid water than Earth, hidden beneath kilometers of ice. For astrobiologists, it is one of the most promising places to search for extraterrestrial life. Enceladus, a small moon of Saturn, offers a similar mystery. Despite its modest size, Enceladus has captivated scientists by spraying plumes of water vapour and ice grains from cracks near its south pole. These geysers erupt hundreds of kilometres into space, and spacecraft have even flown through them, detecting organic molecules mixed with the ice. Like Europa, Enceladus appears to harbour a subsurface ocean kept liquid by internal heat. Its geysers are like windows into that hidden sea, offering a tantalising glimpse of what lies beneath. To think that a moon barely 500 kilometres across could sustain an ocean beneath its frozen crust is one of the solar system's great surprises. Even more distant worlds carry water in strange forms. Pluto, once considered the 9th planet and now recognised as a dwarf planet, is covered with nitrogen ice and water ice mountains that rival the Rockies in scale. Its surface is dynamic, with glaciers of frozen nitrogen flowing across plains. Data from the New Horizons mission revealed a heart-shaped region of Pluto where ices flow and churn, creating a landscape far more active than expected for such a small, cold world. Water ice on Pluto acts as bedrock, so rigid in the extreme cold that mountains can rise and persist for eons. Here, water has become more like stone, a reminder of how context transforms its nature. Beyond Pluto, in the Kuiper Belt and the Oort cloud, countless icy bodies drift through the darkness. Comets, when nudged inward, display the sublimation of these ancient ices as glowing tails. They are time capsules carrying water that formed billions of years ago, and some of them may have delivered part of Earth's own supply. These frozen travellers remind us that water is not unique to Earth, but a common thread woven throughout the solar system. Ice behaves differently depending on its environment. On Earth, it floats, expands as it freezes, and melts into liquid that nourishes rivers and lakes. On moons like Europa, it forms a thick shell over an ocean, shifting and cracking under gravitational stress. On Pluto, it is so strong that it mimics the behaviour of rock. Scientists have identified at least 18 different crystalline structures of ice, each stable under different pressures and temperatures. In some conditions, water ice is denser than liquid water, sinking instead of floating. These exotic forms of ice exist in the deep mantles of icy moons and giant planets, a reminder that even a substance as familiar as frozen water can surprise us with alien complexity. What unites glaciers on Earth with ice on distant worlds is their role as reservoirs. They store water in forms that seem static but are in fact part of larger cycles. On Earth, glaciers release meltwater that feeds rivers, while on Enceladus, ice plumes release material into Saturn's rings. On Pluto, glaciers of nitrogen flow slowly across the surface, redistributing frozen material. Each world has its own frozen cycle, a choreography written in ice. The symbolism of ice is also powerful. To humans, it represents purity, clarity, fragility, and endurance. Yet scientifically, it is also a puzzle, revealing the ways in which a simple molecule can create landscapes, regulate climates, and possibly even support alien life. When explorers look at Europa's cracked surface or Enceladus's geysers, they see more than ice. They see the possibility that somewhere beneath, chemistry may have taken the same leap it once did on Earth, from molecules to biology. In this way, glaciers and ice worlds are not just frozen remnants of the past, but possible windows into the future of exploration. They remind us that water, in all its forms, is universal, shaping worlds both familiar and alien. Whether grinding through a mountain range on Earth or lurking beneath the icy shell of a distant moon, frozen water remains one of the most dynamic and fascinating materials in the cosmos. To gaze at a glacier or a photograph of Europa is to see patience in solid form. It is the same molecule that flows in rivers and fills clouds, but here slowed, stiffened, and preserved. Ice records the past in its layers, carries the present in its movements, and hints at futures still hidden beneath its surface. On Earth, glaciers are melting, reshaping coastlines and challenging societies. Elsewhere, frozen oceans may await discovery, holding secrets beneath their silent crusts. Water's frozen faces remind us that even in stillness, there is always change, and in every shard of ice, a story of worlds both known and unknown. When scientists dream of life beyond Earth, their first question is often simple: where is the water? Not because life necessarily requires oceans and rivers exactly like ours, but because every form of life we know depends on liquid water as its essential medium. To find extraterrestrial water is to find the possibility of biology, and so the search stretches across planets, moons, and even into the icy reaches of the solar system. Mars is the most evocative of these quests. Today, it is a cold desert, its atmosphere thin and dry, its surface scoured by winds that leave dust storms swirling across rusty plains. Yet the scars of water are everywhere. Deep valleys, winding channels, and fan-shaped deltas suggest that liquid once carved its way across the Martian surface. Minerals found in Martian rocks show chemical signatures that can only form in the presence of water. Billions of years ago, Mars may have had lakes, rivers, and perhaps even oceans, with conditions that could have supported microbial life. The mystery lies in where all that water went. With a weaker gravity than Earth, and no strong magnetic field to shield it, Mars slowly lost much of its atmosphere to space. Without a thick blanket of gases, liquid water could no longer persist on the surface. It would freeze or evaporate almost instantly. Some of it may still linger underground, locked in permafrost or briny aquifers. Seasonal dark streaks seen on Martian slopes called recurring slope lineae once raised hopes of present-day trickles, though later evidence suggested dry flows of dust may be the culprit. Even so, orbiters and rovers continue to hunt for clues, drilling, sampling and scanning for hidden reservoirs that might still exist below the surface. If Mars once held oceans, the idea that life could have started there becomes tantalizing. Microbes might have thrived in warm springs, hydrothermal systems, or beneath ice-covered lakes, shielded from radiation. Even if Mars is sterile today, the fossils of its watery past may be preserved in rocks, waiting for future missions to uncover them. The red planet is a reminder that planets change, and that water can come and go, leaving behind both landscapes and questions. Beyond Mars, the outer solar system holds some of the most promising candidates for alien oceans. The icy moons of Jupiter and Saturn may seem frozen and inert from afar, but appearances deceive. Beneath their icy crusts, vast hidden seas may slosh in darkness, warmed not by sunlight but by tidal flexing and internal heat. Europa, a moon of Jupiter, has been a beacon of curiosity since spacecraft revealed its cracked, ridged surface in the 1970s. Its icy shell is thought to float on a global ocean that may be over 100 kilometers deep. The ridges and chaotic terrain suggest that the ice is shifting and interacting with liquid water below. If this ocean exists, it contains more water than all of Earth's oceans combined. Heated from within by the constant gravitational tug-of-war with Jupiter and neighbouring moons, Europa's interior may sustain hydrothermal vents, just as Earth's deep oceans do. And where there are vents, there may be the chemical recipes for life. Saturn's moon Enceladus, though far smaller, has revealed itself in spectacular fashion. Geysers erupt from cracks near its south pole, spraying plumes of water vapour and ice particles into space. These plumes are direct evidence of a subsurface ocean, venting into the void. When the Cassini spacecraft flew through them, it detected salts and organic molecules, the very ingredients that make scientists' imaginations race. If Enceladus can shoot its ocean into space, then sampling for life may one day be as simple as flying through its frozen mist. Other icy moons carry their own possibilities. Ganymede, the largest moon of Jupiter, may harbour a layered ocean beneath its thick ice. Callisto, another Jovian moon, shows hints of subsurface water as well. Even distant Titan, Saturn's largest moon, while famous for its methane lakes on the surface, may conceal a water ocean beneath its crust of ice and hydrocarbons. Each of these worlds expands the definition of where life might take root, showing that water need not be on the surface under a warm sun to be biologically important. Further out still, even dwarf planets like Pluto show signs of possible subsurface oceans. Data from the New Horizons mission revealed a surface of nitrogen ice and a fractured crust that suggests an underlying reservoir of liquid water mixed with antifreeze-like compounds. If water can persist so far from the sun, then it may be widespread in places long dismissed as barren. The search for alien oceans is more than just cataloguing where water might be. It is also a shift in perspective. For centuries, humanity assumed Earth was unique in its blue abundance. Yet again and again, we've discovered that water, in one form or another, is surprisingly common. The challenge is not finding it, but finding it in liquid form, stable long enough to nurture chemistry into biology. Modern missions are designed with this goal in mind. Rovers on Mars drill into rocks in search of hydrated minerals. Orbiters around Europa and Enceladus scan for magnetic signals and surface features that betray hidden oceans. Future probes may one day land on the ice, melt their way downward, and send robotic explorers into alien seas. The dream of finding life beyond Earth may hinge on these watery worlds. What makes this pursuit so captivating is the universality of water's story. On Earth, it enabled chemistry to cross the threshold into biology. In the solar system, it may be doing the same in unseen places. If microbes are found beneath Europa's ice, or in the plumes of Enceladus, it would suggest that life is not rare but perhaps inevitable wherever water endures. A discovery like that would change not only science, but humanity's sense of place in the cosmos. Even without confirmed biology, the idea of alien oceans reshapes our imagination. They remind us that life need not look like Earth's to be possible. In darkness, beneath kilometers of ice, alien chemistries could be at work. Strange ecosystems might exist, illuminated not by sunlight, but by the glow of hydrothermal vents. Creatures, if they exist, might never see the stars yet thrive in eternal night. Water beyond Earth forces us to reconsider the boundaries of habitability. It suggests that the universe may be more generous with life than we once believed. The question is no longer whether Earth is unique in having oceans, but whether those oceans elsewhere are silent or alive. Every droplet, every plume, every icy crust in the solar system is a reminder that water is not just Earth's story, but a cosmic one. To search for alien oceans is to follow the thread that connects us to distant worlds. Worlds where chemistry may still be rehearsing the steps that once played out in Earth's own seas. In that sense, water may be both the most familiar and the most alien substance in the universe. The bridge between rocks and life, between planets and possibilities. Humanity's story has always been tied to water, and the future will be no exception. If the rivers of the past were the cradles of civilization, then the choices made about water in the coming centuries may well determine the shape of global society. Scarcity, innovation, and the shifting climate will all play roles in this unfolding chapter, with water standing at the centre as both challenge and possibility. Scarcity is already one of the defining issues of our time. Out of all the water on Earth, only a tiny fraction is fresh, and most of that is locked in glaciers or hidden deep underground. What remains must serve billions of people, countless ecosystems, and an ever-growing demand from agriculture and industry. By some estimates, nearly 1 in 4 people today live in regions of high water stress, where demand outpaces reliable supply. For many, turning on a tap is not an everyday certainty but a fragile luxury. The causes of scarcity are complex. Population growth drives up demand, while groundwater reserves are being drained faster than they can be replenished. Rivers that once surged to the sea are sometimes reduced to trickles by the time they reach their mouths. The Colorado River in North America, the Yellow River in China, and the Indus in South Asia all struggle to meet the needs placed upon them. Aquifers, such as the Ogallala beneath the American plains or reserves beneath northern India, are falling by meters each year in some places. It is a reminder that water, though renewable in theory, can be consumed as unsustainably as oil or coal when the balance of use and replenishment is ignored. Climate change intensifies these pressures. Warmer temperatures accelerate evaporation, altering rainfall patterns and shifting storm tracks. Some regions grow wetter, while others face prolonged drought. Glaciers that feed rivers are retreating, threatening the seasonal flows that billions rely on. The Himalayan glaciers, often called the Third Pole for their immense ice reserves, supply water to nearly 2 billion people through rivers like the Ganges, Indus and Brahmaputra. Their decline carries profound consequences for Asia's future. Similarly, the Andes glaciers sustain rivers that feed cities and farmland across South America. Their retreat is already reshaping life in those regions. Sea level rise adds another twist. As the oceans creep inland, they salinate freshwater aquifers near coasts, making wells undrinkable. Low-lying nations and coastal cities are particularly vulnerable, facing the dual challenge of flooding and loss of freshwater resources. The irony is sharp. Surrounded by rising seas, yet deprived of fresh supplies. Despite these looming challenges, water also offers paths of hope. Desalination is one such path. The process of removing salt from seawater has moved from ancient experiments with solar evaporation to modern plants that can produce billions of litres of fresh water each day. Countries like Saudi Arabia, Israel, and the United Arab Emirates rely heavily on desalination to support cities and agriculture in arid climates. Advances in reverse osmosis technology have reduced the energy costs, making desalination more accessible. Still, it remains expensive and energy-intensive, and its environmental impacts, such as the disposal of concentrated brine back into the sea, must be managed carefully. If sustainable solutions are found, desalination could become one of humanity's most important tools for adapting to scarcity. Equally promising are innovations in water recycling and efficiency. Wastewater treatment plants can now purify sewage to drinking standards, a concept often summarized as toilet to tap. While the phrase may not sound appetizing, the water produced can be cleaner than traditional supplies. Cities like Singapore have embraced this approach, reducing dependence on imports and rainfall. In agriculture, which consumes the vast majority of fresh water, techniques like drip irrigation and precision watering drastically cut waste. Farmers equipped with sensors and data analytics can optimize irrigation to match crops' exact needs, saving both water and money. Conservation too holds enormous potential. Small changes multiplied across billions of people can make a significant difference. Fixing leaks in municipal systems prevents vast amounts of loss. Protecting wetlands ensures natural filtration and flood control. Restoring rivers and aquifers allows ecosystems to function as buffers, absorbing the shocks of drought and flood. The future of water will not depend solely on grand engineering projects, but also on countless small, deliberate acts of stewardship. Water will also continue to play a role in cooperation and in conflict. Shared rivers and aquifers cross borders, linking nations whether they like it or not. The Nile Basin, for instance, connects 11 countries, each with its own needs and ambitions. Tensions have risen as Ethiopia builds the Grand Renaissance Dam, altering flows downstream. Yet these same shared waters have also driven dialogue and treaties, reminding nations that compromise is often the only viable option. In a future where water scarcity intensifies, diplomacy over water may become as important as diplomacy over oil once was. It is also worth remembering that water carries cultural and symbolic power. As societies adapt to changing supplies, they will not only engineer solutions but also redefine their relationship with water. Already, some legal systems recognize rivers and lakes as entities with rights, echoing indigenous perspectives that view water as a relative rather than a resource. Such shifts may prove essential in fostering sustainable attitudes, where protection of water is seen not as an obligation but as an act of respect. On a global scale, the future of water is bound up with the future of climate. Oceans absorb much of the excess heat trapped by greenhouse gases, buffering us from even more rapid warming. They also absorb carbon dioxide, altering their chemistry and threatening marine ecosystems. The health of the planet's water systems will determine the health of its climate, and vice versa. Efforts to mitigate climate change, from reducing emissions to restoring forests, are at the same time efforts to protect water. For all the difficulties, there is resilience in water's story. It cycles endlessly, shifting between forms but never vanishing. Human ingenuity has already found ways to store it, move it, clean it, and even create new supplies from the sea. The challenge is not that water will disappear, but that it will not always be where we want it, when we want it, in the quantities we demand. Meeting that challenge will require cooperation, adaptation, and humility. Imagine the future city that thrives on sustainable water. Its rooftops capture rain, its pipes recycle wastewater, its agriculture is efficient, and its rivers are restored rather than diverted. Its people treat water not as disposable but as sacred, recognizing its rarity and worth. Such cities are already emerging in small ways, from desert metropolises to coastal hubs. They are glimpses of a future in which water scarcity is not a crisis but a catalyst for innovation. The story of humanity and water is still unfolding. Scarcity will test us, but solutions exist. Climate change will reshape supplies, but adaptation is possible. Desalination, recycling, conservation and cooperation can all turn challenge into opportunity. Water, after all, is the great teacher of persistence. It flows around obstacles, adapts to new paths, and endures through every cycle. Humanity, if wise, can do the same. In the centuries to come, the measure of progress may not be skyscrapers or spacecraft, but how societies secure and share clean water. The future will not be defined by conquering water, but by learning to live with it, carefully, creatively, and with respect. Just as rivers nurtured the first civilizations, the choices made about water now will shape the civilizations yet to come. Water is more than a liquid. It is a thread woven through every moment of Earth's story. To watch it ripple across a lake or fall as rain is to glimpse a substance that has travelled farther and endured longer than imagination can easily grasp. Every drop has lived countless lives, as vapour rising from volcanic steam, as snow pressed into glaciers, as ice drifting on comets billions of years ago. To drink a glass of water is to take part in this endless circulation, sharing in a journey that has flowed since the dawn of time. As a timekeeper, water is unmatched. Its cycles are clocks that mark the rhythms of the planet. The steady rise and fall of tides follow the pull of the moon, their cadence older than human history. The annual return of rains defines seasons, shaping migrations, harvests, and traditions. Even the drip of a melting icicle marks time, second by second, drop by drop. Glaciers preserve histories in their layers, storing traces of ancient atmospheres, volcanic eruptions, and cosmic dust. A core of ice drilled in Antarctica reads like a library of climate, a record of hundreds of thousands of years written in frozen pages. Yet water is also a traveller, restless and tireless. It moves from cloud to sea, from river to aquifer, from living cell to atmosphere, never pausing for long. The same molecules that once floated in the air above dinosaurs now fall as rain on modern cities. A droplet that once coursed through the veins of a tree might today swirl in the open ocean. Water is the planet's most persistent migrant, never bound to one place, always seeking the next transformation. As a storyteller, water speaks through landscapes. It carves canyons, etches river valleys, and lays down sediments that become rock. Each bend in a river tells of centuries of meandering. Each ripple in sandstone records waves of a vanished sea. Oceans whisper their stories in shells that collect on beaches, their patterns shaped by creatures that lived and died long ago. Even fossils preserved in stone are memories of organisms once sustained by water. Through its ceaseless motion, water inscribes history onto the surface of the earth, leaving behind chapters in stone, ice, and sand. The universality of water gives it a kind of poetry. It is both humble and cosmic, ordinary and miraculous. The drop that quenches thirst may once have been frozen in the shadowed crater of the moon. The snowflake falling on a mountaintop may be made of atoms forged in a distant star. Water links the cosmic to the intimate, the universe to the glass in your hand. There is also a paradox in its character. Water is soft and yielding, yet powerful enough to wear down mountains. It is transparent, yet it holds the colours of the sea and the sky. It sustains life gently, yet it can sweep it away in floods and storms. It is a patient sculptor, working slowly but also a sudden force, capable of reshaping landscapes overnight. Its poetry lies in these contradictions, in being at once fragile and unstoppable. Human culture has always mirrored this duality. Myths speak of floods that erase worlds, but also of springs that bring renewal. Poets have compared rivers to time, oceans to eternity, rain to memory. Water appears in rituals of purification, in metaphors of change, and in songs of longing. We return to water again and again because it captures something fundamental, the sense of being part of a larger flow, of belonging to a story greater than ourselves. When you lift a glass to your lips, the water inside is older than humanity. Some of its molecules may have fallen as rain on the first forests, or frozen in glaciers during the last ice age. Others may have drifted in comets before Earth was born. In that simple act of drinking, you join hands with history and prehistory alike. The water does not care who you are, yet it carries within it the memory of all that has been. Even within our own bodies, water serves as a reminder of connection. More than half of what we are is water, moving through our veins and cells, constantly refreshed from the world outside. To live is to be part of this flow, to borrow water for a time before releasing it again into the cycle. Our tears, our sweat, our breath are small contributions back to the great river of life. The poetry of water also lies in its endurance. Long after civilizations crumble, rivers will still carve valleys. Long after monuments fall, glaciers will still flow. Even when stars fade and worlds freeze, water will remain, drifting as ice among the galaxies. It is older than mountains and will outlast cities. To contemplate water is to feel both the brevity of human life and the vastness of time. And yet, for all its grandeur, water remains intimate. It is the comfort of a warm bath, the relief of a summer rain, the quiet rhythm of waves on a shore. It is the first thing offered to a guest, the last gift to the dying. Its poetry is not only cosmic but personal, written in everyday gestures that connect us to each other and to the world. To call water a timekeeper, a traveller, and a storyteller is not merely metaphor but truth. It marks the hours of the planet, moves endlessly across space and time, and inscribes its history into every stone and shell. The drop you drink today may have once been steam rising from a volcanic eruption, or ice clinging to a comet billions of years ago. Each drop is a relic of journeys too vast to imagine, yet intimate enough to touch your lips. In this way, water is the closest thing we have to immortality. It endures through every change, flowing from past to present to future without end. To listen to its rhythm, to follow its course, is to hear the poetry of the planet itself, the endless patient verse of a world shaped and sustained by water. Water's story is, in truth, the story of everything. It is older than the Earth itself, stitched into the universe from the simplest elements forged after the Big Bang. Hydrogen, the lightest atom, came first, and oxygen was born in the fiery hearts of stars. When the two finally met in the coldness of space, They formed a molecule that would become the quiet architect of worlds. From interstellar clouds to comets, from volcanic steam to planetary oceans, water has been a constant traveller, carrying with it both the memory of origins and the promise of life. On Earth, water was not only delivered but also transformed into oceans that shaped the face of the planet. Seas filled the basins, rivers carved the land, and glaciers sculpted mountains into valleys. Over billions of years, water has been the patient artist, etching coastlines, building deltas, and laying down the sediments that would later tell stories in stone. It is both delicate and mighty, able to wear down granite with nothing more than persistence. The landscapes we walk today are water's signature, carved in liquid ink over geological time. But water's greatest achievement was in chemistry. In its embrace, simple molecules found room to mingle, collide, and assemble into something more. Hydrothermal vents, tidal pools, and primordial oceans became the laboratories where prebiotic chemistry played its experiments. Without water's peculiar properties, its solvent power, its hydrogen bonds, its ability to stabilize fragile molecules, life could never have taken hold. Cells are still tiny oceans, each filled with water that echoes the seas in which their ancestors first swam. To this day, every living thing is, in essence, a vessel for water's chemistry. As life grew more complex, water remained the medium of evolution. The Cambrian seas were crowded with trilobites, worms, and the first predators, all borne by currents and tides. Fish evolved fins and jaws in the oceans before some ventured onto land, carrying water inside their bodies as a reminder of their birthplace. Even humans are walking testaments to aquatic origins. The salt in our blood, the fluid that cushions our joints, and the watery sacs that cradle embryos all recall the primordial seas. Life did not just begin in water, it has never really left it. Civilizations too rose by the rivers. The Nile, the Tigris and Euphrates, the Indus, the Yellow River, each provided more than irrigation and fish. They gave order, predictability, and the possibility of surplus. From those surpluses came writing, cities, and culture. Water was the first infrastructure, the original highway, the shared resource that required cooperation and ingenuity. Aqueducts, qanats, canals, and wells are monuments to humanity's long partnership with water. Entire societies bloomed when they learned to manage it, and entire empires faltered when they failed. Yet water is more than a resource. It has always carried symbolic and spiritual weight. Cultures have revered it as divine, sacred, or purifying. It has been the river that cleanses sins, the spring that grants visions, the flood that destroys and renews. Its power lies not only in quenching thirst but in inspiring awe. To immerse oneself in water is to feel a connection both physical and symbolic, to take part in a cycle older than humanity itself. Science has gradually unravelled the mysteries of water, but even as understanding deepens, its sense of wonder remains. Ancient philosophers believed it was the fundamental element, the base of all things. They were wrong in detail, but right in spirit. Water is not everything, but everything depends on it. From Newton's laws explaining tides to satellites mapping the global water cycle, from chemistry labs studying hydrogen bonds to probes, discovering icy plumes on Enceladus, water has continually pushed us to refine our knowledge. Its simplicity hides endless complexity. Its familiarity disguises its strangeness. In the modern age, water is at once abundant and scarce. Oceans stretch across 70% of the planet, yet the share of fresh water accessible for drinking is a fraction of a fraction. Industrial use, agriculture, and expanding cities place immense pressure on rivers and aquifers. Climate change alters rainfall, melts glaciers, and raises seas, unsettling a cycle that once felt dependable. Water has become a challenge, a source of tension, but also a driver of innovation. Desalination plants, recycling technologies, and smarter irrigation are among the many tools humans are developing to meet that challenge. The future of water will test humanity's ability to balance demand with respect, necessity with sustainability. Beyond Earth, water stretches the imagination still further. Mars bears the fingerprints of ancient rivers and lakes, whispering of a time when the red planet was blue. Europa and Enceladus conceal vast oceans beneath ice, their hidden waters warmed by the tug of gravity and the heat of their interiors. Pluto's frozen plains and comets' icy tails remind us that water is not confined to Earth, but is scattered across the solar system, waiting in strange and alien forms. To find water elsewhere is to find possibility, the chance that chemistry has crossed the threshold into biology on worlds far from our own. And yet, for all its vastness, water is personal. It is the rain that streaks down a window, the glass that quenches thirst, the wave that laps at bare feet on a shoreline. It is the snowflake melting on a child's tongue, the steam curling from a cup, the tear that slips down a cheek. Each of these is part of the same cycle, the same molecule endlessly recycled across time. The drop you drink today may once have been frozen in a glacier, drifted in a cloud above the Sahara, or fallen as rain on a Jurassic forest. In water, intimacy and eternity meet. To reflect on water is to reflect on connection. It links the Earth's systems into one whole: atmosphere, lithosphere, biosphere, and hydrosphere, bound together by flows of liquid and vapour. It connects generations, for the water of the past is the water of the present. It connects Earth to the cosmos, for the molecules here are kin to those drifting in interstellar clouds. It connects each person to every other, as the same molecules that move through one body today will pass into another tomorrow. Water is the thread that ties existence together. And so, as this journey through water's story comes to a close, it is fitting to pause with a sense of calm. Every wave that rises and falls, every river that meanders to the sea, every raindrop that clings to a leaf is part of a story older than Earth still flowing. The oceans may roar, glaciers may groan, and rivers may rush, but beneath it all is a steady continuity, the endless cycle of water, always moving, always renewing. To sit quietly and listen to rain or waves is to hear time itself speaking in the language of water. It is a reminder that while civilizations rise and fall, while climates shift and continents drift, the flow endures. Water is cosmic, earthly, vital, and eternal. To know it is to glimpse something greater than ourselves, something that unites stars and streams, comets and clouds, glaciers and glasses on kitchen tables. The story of water is not finished, nor will it ever be. It is still being written in every storm, every trickle, every droplet, and as long as it flows, life, in one form or another, will follow. To watch it move is to see the patient heartbeat of the planet and the quiet rhythm of the universe. And in that rhythm lies comfort, a promise that the story of water, older than Earth itself, will continue long after us, still flowing, still shaping, still telling its tale.